Hi everyone. So in the last lecture we studied about Hertzian dipole antenna. So we see the average power, we saw the radiation resistance, power radiated, and we saw the radiation pattern as well. And then we defined half power beamwidth and full null beamwidth. So those things we have studied about Hertzian dipole antenna. Now we need to study about those dipole antenna whose length is greater than lambda by 10. For Hertzian dipole antenna, the length was less than lambda by 15. Now we need to study about length when greater than lambda by 10. So length is greater than lambda by 10. Those kind of antenna we need to see, and those are known as linear antenna. If your length is greater than lambda by 50, then it is your linear antenna, and if your length is less than lambda by 50, then it is known as Hertzian dipole antenna. This is linear, this is Hertzian. Now in linear antenna we need to study those cases where the length is greater than lambda by 10. In this case we need to study only those cases where the length is greater than lambda by 10. Okay. So two types are there, dipole and monopole. This I have already taught, right? Dipole antenna and monopole antenna. So dipole antenna are center fed and monopole are base fed. So in case of monopole antenna, this is the simple dipole antenna that we have already studied. But in case of monopole antenna, what we will do is that our supply will be just above the ground, and there will be only one arm of antenna. Only one arm of antenna would be there, and this would be ground, or you can say perfect conductor. Either it would be ground or you can say perfect conductor. Anything can be mentioned. They can write down ground as well, or they can write down perfect conductor as well, because ground is a perfect conductor. Now one interesting thing here, what will be the range of theta? Because let's just say this is your z axis. So here what you are doing, you are completing the complete cycle. No, this is your z axis, this is what I am saying, z axis. So you are completing the complete cycle, right? So value of theta is from 0 to 180 degree, complete 0 to 180 degree. This is the range, right? But what about this guy? What will be the range of theta here? Let's just say this is placed along z axis. So from 0 to 90 degree only you are coming. Like you are not able to complete the whole path. Here there is one arm of antenna, there is two arms of antenna. So one complete path if you do, that means you are walking around 180 degree. But here you will start from here and everything ends here, because this is the ground. No, after that there will be no radiation. Let's just say this antenna radiates. So it can radiate here, 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 here. It can radiate here, but it can radiate till 90 degree range only. It cannot radiate more than 90 degree range. Is that clear to you? But here it can radiate till 180 degree range. So here the value of theta would go from 0 to 90 degree. A very important point. It will be used somewhere in our analysis. Okay. So let's start studying about a dipole antenna. So first I am taking a case of random dipole antenna, random linear dipole antenna whose length is L, which is greater than certainly lambda by 10. So if this is length L, then this would be L by 2 and this would be L by 2, and this is our source, that is I naught cos omega t, and at P point we need to find H phi s, E theta s, all those points we need to find. Why we are finding these points? Because after that we need to find P average and P radiated. This is our target, and then we will make a radiation pattern. So I hope you are clear with Hertzian dipole antenna lecture, then you would know which path we are following. So what we need to write? First we need to write H phi s and E theta s. In Hertzian dipole case as well we wrote it down. What was our H phi s? So let's write it down. What did I tell you? IDL sin theta upon 4 pi r j beta e to the power minus j beta r a r cap. This was our H phi s, and for E theta s you just need to multiply by neta, and direction will also say, sorry, here it was a phi, really sorry, it was a phi. Now there we derived it, but here we do not need to derive. No one will ask you this. Okay, no one will ask you the derivation, but expression is important. So what will be the expression? The expression will be j, this j, I naught upon 2 pi r, j I naught upon 2 pi r. Here I naught upon 4 pi r was, I naught upon 4 pi r was there, no? So here I naught upon 2 pi r, and this j is also coming. Then into f theta e to the power minus j beta r a r cap. Is that clear? And here what will be happening? Same thing, just multiply with neta, not AR. Again I am doing this mistake. AR cap is the direction of radiation, right? The direction of a field. Direction of magnetic field is A phi cap. And what about electric field? Electric field is in theta direction. And how will you write it down? Just you need to multiply with neta. Same expression, just multiplied with neta. Nothing else. Same expression, just multiplied with neta. And direction is in theta. Neta is the intrinsic impedance, right? Now what is this f theta? That we need to define now. So what is this f theta? So I will write down the expression, and that you need to keep in mind. So f theta is cos beta L by 2 cos theta minus cos beta L by 2 divided by sin theta. This is your f theta. You need to keep in mind. It's not that tough. Let me tell you how do I remember it. So anyway, I need to remember this first term, cos beta L by 2 cos theta, because this is length L, this is L by 2, this is L by 2. What is the angle theta? Theta is the angle between the arms of antenna and AR cap. So this first term I remember, cos beta L by 2 cos theta. Then when I write down in minus, then I will write down this much, cos beta L by 2. Are you getting this point? Cos beta L by 2 cos theta, that I remember. And when I write down in minus, then I will write down this much value. And when I write down something in denominator, this was in numerator, then I will write down in denominator. So this has been already written. Now this is left. So instead of cos, I will write down sine, because I am writing something in denominator. In numerator, I am writing this. Denominator, I will write down sin theta. So how I will start? That's our cos beta L by 2 cos theta, that I already remember, minus this much thing, cos beta L by 2. Now what is left? This cos theta is left, but I am writing downward, so sin theta. So anyway, you need to keep in mind, and I don't think this will be too tough to remember. This should not be too tough to remember, right? This is very easy, and even if you forget, then at least you remember this formula, no? So from there you will say that, sir, only I need to pick this one. Just here it would be 2 pi r and j would come. That's it. So anyway, you need to remember this formula. That's it. This is the last thing I am asking you to remember. In Hurrian dipole, I asked you to remember the expression of h phi s. Then you can directly write down E theta s. I did not ask you to remember the expression of P average. I asked you to remember the expression of P radiated as well. What was the P radiated there? 80 pi square dl by lambda whole square under root mu r by epsilon. This was your R radiated. So P radiated you can directly write down into I naught square by 2. That would be your P radiated. So these are some important expression that should be there in your mind. So h phi s is j I naught upon 2 pi r f theta. In place of f theta, you need to write down this thing, e to the power minus j beta r. So these can be there in your mind. Now let's take the special cases like half wave dipole, quarter wave dipole. When I say half wave dipole, that means length is equals to half wavelength. Half wave dipole. If I say quarter wave dipole, means length is equals to lambda by 4. If I say full wave dipole, that means length is equals to lambda. So can you try writing all these expressions? You just need to put L equals to lambda by 2. That's it. So this complete length is lambda by 2. So what will be half length? Half length lambda by 4 and lambda by 4. So whenever I see question on linear dipole antenna, my first task is always writing down f theta. No matter what kind of question is there, I will always write down f theta. This is my first task. So that would be cos beta. Beta is 2 pi by lambda. Cos beta L by 2. So this is length L, this is L by 2. Cos beta L by 2. Cos theta. Cos beta L by 2 cos theta minus cos beta L by 2, again the same thing, divided by sin theta. So cos pi by 2 is 0. So this term will be gone. So what you are left with? Cos pi by 2 cos theta divided by sin theta. So this is your f theta, but certainly it is for a special case, that is for half wave dipole. Since we are going to use it again and again, then this will be in your mind. What I am saying is that you will be eventually remembering this expression, cos pi by 2 cos theta divided by sin theta, because I will be again and again using it. So generally for half wave dipole, we remember f theta expression. We don't need to derive it. You can derive it as well if you want to. Like this is simple one step expression only, but eventually a lot of people remember it only. Okay. So yeah. Now let's write down h phi s. So what will be your h phi s? So h phi s will be j I naught. I naught is the peak current, j I naught upon 2 pi r. Then f theta, that is f theta. Let's keep f theta as it is. J I naught upon 2 pi r f theta e to the power minus j beta r a phi cap. And what about E theta s? J I naught, J neta I naught, J neta I naught upon 2 pi r f theta e to the power minus j beta r a theta gap. Not tough to write. Certainly it is not tough to write, right? Okay. So HYS E theta s expression we have written. Now what about the current distribution? So in our Hertzian dipole antenna, what did we say? The length is pretty small. We assumed length to be lambda by 100. If length is pretty small, then that means on standing wave, on standing wave pattern of current, this much width will be very small. If this much width is very small, that means current distribution is uniform. This is what we said. In Hertzian dipole, the current distribution is uniform. Why is that so? Because the length is pretty small, and if the length is pretty small, that means across the length current is not changing much. But here the length is decent enough, that is lambda by 2. So if you talk about the current, how will the current pattern look like? Here minima, then maxima, then again minima. So how much is this length? Lambda by 2. So now let's just say here there is zero current. So the current will be going like this for lambda by 2 length. For which length? Lambda by 2 length. This will be the current distribution. Why is that so? Because the length is pretty huge now. The current will be changing. Like at this point of current, if you are having maxima, then here, so at this point of current you are having maxima. So after lambda by 4 you will have your, again I am saying it wrong. At this point, if you are having your current minima, then after lambda by 4 you will be having maxima. Then after again lambda by 4 you are having your minima. So in that manner we are going, right? Minima, maxima, minima. So there is certain amount of length. If the length is huge enough, that means you are getting enough space and your current distribution will be changing. So here current distribution is not uniform. That means it will change with respect to the space as well. Like if I say here the current is 50 ampere, then if I ask you what will be the current here, then you cannot comment. You will say that sir, it can vary with respect to the space. That means across the length of antenna, you can get different currents. There the current is not same. But in Hertzian dipole, if I ask you that the current here is 10 ampere, then what will be the current here? You can say it is 10 ampere only, because across the length of the antenna, the current doesn't change much. But in case of half wave dipole, or in case of linear dipole only, in case of linear dipole antenna, whether it is lambda by 2 or lambda by 4 or lambda by 8, these are finite length, these are good enough length, and across these lengths certainly your current can change. So you cannot say the current distribution is uniform. So these kind of statements can come in the examination to tell that whether the statement is true or not. So they will ask that on the arms of half wave dipole antenna, the current distribution is uniform. Is that correct? No. On the arms of half wave dipole antenna, the current distribution is uniform. No, it is not uniform, it is sinusoid. So current distribution on linear dipole antenna is not uniform, it is sinusoid. Now I have written it for linear dipole antenna. That means whether it is lambda by 2 or lambda by 4 or lambda by 8, anything, if the length is greater than lambda by 10, then certainly you will say that it will not be uniform. It could be sinusoid, it could be like this, it could be like this, it could be like anything, but certainly it will not be uniform. If I am making like this, that means it is uniform. I am saying that always the current is I naught. But here at some time you can have I naught, at some time you can have minus I naught, at some time you can have I naught by under root 2, because the length is finite enough, right? Okay. Now time average power. So what is the formula? 1 by 2 real of ES cross HS conjugate. Now do you think here ES is the theta component and H is the phi component. Now do you think you need to put these values, and that will be very complex. No need to remember all these things. I am not going to put these values, right? That would not make any sense. That if I put these values and if I get any expression, so from there I am not getting any fruitful. So just I am writing down this step only, that if any day there is only 0.1% chance that they will ask you these kind of questions, but if any day you need to calculate P average for half wave dipole antenna, then you know how to write down HYS, then you know how to write down E theta S, you simply need to do the cross product, right? Or what could be the other expression? E naught square by 2 neta. That means, so this we have seen in our EM wave as well, in waveguide as well, and now we are seeing it in antenna as well. So E theta square divided by 2 neta. So mode of E theta square divided by 2 neta. What will be the direction? Direction will always be in the direction of radiation, because the direction of time average Poynting vector is always in the direction of propagation or in the direction of radiation. And what is the other formula? The other formula is 1 by 2 neta h phi s whole square, and direction is always in the direction of radiation. Is that clear to you? Well and good. So these are the formula. Anyway, any formula we can use, depends on the problem that they are asking. Okay, certainly we will solve these kind of problems as well. P radiated. So when we do all these kind of calculation and everything we do, then a certain answer we get for P radiated, and that you need to keep in mind. So that answer is I naught square by 2, that is the current, I RMS current is there, into 73 ohm, and certainly mu r under root mu r by epsilon r will also come because of the medium. So this is the P radiated. So what did you understand? What is your R radiated here? My R radiated is 73 into mu r by epsilon r ohm. So if you are sleeping someday and I wake you up and I ask you what is the radiation resistance for a half wave dipole antenna, you should tell me, sir, 73 ohm. Not only 73 ohm, sir, if medium is different, then under root mu r by epsilon r. If you are sleeping and I ask you and I wake you up and I ask you what is the radiation resistance of a Hertzian dipole antenna, you will say that, sir, it is 80 pi square dl by lambda whole square. This is for air, but for medium under root mu r by epsilon r. Should be there in your mind. Certainly we will write down in summary as well, but it should be there in your mind. Is that clear? Another thing that you need to keep in mind, you don't need to remember P radiated. I never remember P radiated. I only remember the formula of R radiated, because if I know R radiated, I can certainly find P radiated. And I hope you know what is R radiated. R radiated is like that if my source is applying, if my antenna is radiating some power, that means my source is applying that power, so I can replace my antenna with a particular resistance. So that if I replace it by that resistance, then how much power that resistance is dissipating. So the same amount of power that resistance is dissipating, the same amount of power antenna is radiating, right? So this concept we have already seen. So here I am not making that diagram. So in the previous video as well, what did I say? For Hertzian dipole, what is your Zin? Let's just say this is your transmission line and this is my antenna, and this is my source, and this is my Hertzian dipole. This is my Hertzian dipole antenna. So there I wrote down my Zin is equals to 80 pi square dl by lambda whole square. So here what will be the Zin? That I am asking. So here the Zin is, if let's just say this is your antenna, this is the arms of antenna, and this is the transmission line that you already know, and this is the voltage source which you are exciting with. So here this is your source, right? That is, just a second, someone is knocking at the door, just one. Yeah, sorry for the interruption. So what I was saying, so yeah, there is a source, this is our source, which we are calling as I naught cos omega t. I naught cos omega t, this is our source, this is our transmission line, and this is our antenna. So in Hertzian dipole, we replaced it with 80 pi square dl by lambda whole square. But here we are going to replace it with 73 ohm only. No, there is some reactive element as well, 42.5. So this is the Zin, and certainly ohm will be the unit. So this is the Zin. Now some people will have a doubt that, sir, when you write down radiation resistance here, you only write down the resistive part. You did not write down the reactive part. Why is that so? Can you tell me? So in our EMFT as well and in our network analysis as well, I told you one thing. Whenever we find the power dissipated, if I am finding the power dissipated, then I will only take resistive part in action, right? Because power is always dissipated in the resistor. So when you talk about power dissipated, then you only take a resistive part in action. So what we are doing here is that if I replace my if I replace my antenna with the equivalent resistor, then how much power it will dissipate, the same amount of power it will radiate. From the source, some power will be dissipated, the same amount of power will be radiated by the antenna. This is what we are assuming. So if I am saying the power dissipated in antenna, or you can say power radiated by the antenna, that means I am only taking resistive part in action, right? So I need to take only resistive part in action. But if someone asks you what is the Z in of this particular antenna, then this is the Z in, right? You will get to know whether they want to take you resistive part only or they want to take you the complete Z in. In some of the problems, you will get to know whether you need to take Z in action or you need to take only the resistive part in action. So that you will be getting know. So that's it. That's it about our lambda by 2 half wave dipole antenna. What did we show? HYS, E theta S. There we needed the F theta expression, so that we from here we go to know. We know what is our, we get to know that current distribution will always be not uniform, it would be sinusoid. Time average power you can write down. Then P radiated, one thing I asked you to remember, what is that? That radiation resistance will be 73 ohm. And certainly with medium it could be under root mu r by epsilon r. Well and good. Do the same thing for quarter wave dipole antenna. Right? Quarter wave means length is lambda by 4. And all these are dipole antenna. We are not studying monopole as of now, we are studying dipole antenna. So this is your quarter wave dipole antenna. You can do all the things on your own. Certainly you can try doing it. So what will be your F theta? So here F theta would be cos, and you must be wondering why I did not make radiation pattern. So radiation pattern we will see in the last. In the last we will see radiation pattern of lambda by 2, lambda by 4, everything. So don't worry about radiation pattern. For radiation pattern we will spend 1 hour or more than 1 hour I guess for only radiation pattern. So don't worry about that. Okay. So 2 pi by lambda into here what will come? Lambda by 8 cos theta minus cos, here what will come? Pi by 4 will come. Cos pi by 4 divided by sin theta. Cos pi by 4 cos theta minus 1 by under root 2 divided by sin theta. So no need to remember all these things. Now if I write you H phi s. So if you want to remember this, you can remember this, otherwise it is like you can derive it as well. But it's not possible to remember all this formula. But this is something that we will keep in mind because we will use it again and again. That's why it will be there in our mind. But this is not this is not something that is in our mind always. So yeah, forget about that. You can derive it in this manner. You just need to know the formula of F theta. What is the formula of F theta? Cos beta L by 2 cos theta minus cos beta L by 2 divided by sin theta. So what is your H phi s? That is J I naught upon 2 pi r. F theta, this shows the direction of radiation and this shows the direction of magnetic field. And what about E theta s? Simply you need to multiply with neta. J neta I naught upon 2 pi r. F theta, this shows the direction of radiation and this shows the direction of electric field. Right? What about the current distribution? What do you think? Current distribution will be, again here is also good amount of length is there, lambda by 4. So again it will not be uniform, it would be sinusoid. Sinusoid, or you can say not uniform. Can you write down P average? Same thing is there. 1 by 2 real part of E theta s H phi s conjugate, and then same thing, ditto same thing. I am not gonna write down here, I am not gonna write down these values and get some complex expression, that doesn't matter. P radiated. So what do you think, what is your P radiated here? Here the P radiated is the current that is same, I naught square by 2 into the radiation resistance, that is 73 by 2 here. For lambda by 2 it was 73. For lambda by 4 it is 73 by 2. Right? What about R radiated? This is your R radiated. Same thing is there, just half. And what about Z in? What do you think, what will be your Z in? Ditto same thing, just half. Okay. Z in here, in the previous case, what was the Z in? This was a Z in. Now for lambda by 2, this was the case. If you talk about 42.5 it was, no? I am writing 43.5. It was 42.5. Really sorry. So in the previous case it was what it was. In the previous case it was 73 plus J 42.5. Now the length is lambda by 4. So that you need to keep in mind. For lambda by 2 you remember, and for lambda by 4 you just need to make it half. I will remember for lambda by 2 For lambda by 4, I will just make it half. Same goes for radiation resistance as well. Same thing are there, everything you already know, right? Well and good. So for lambda by 8, what do you think? What will be your answers? You can write down h phi s, you can write down e theta s. This you can ignore as well. No one will ask you lambda by 8, but just I am writing it. Can you write down f theta? Same formula you just need to write down. Cos beta L by 2 cos theta minus cos beta L by 2 divided by sin theta. But what will be the length here? L is lambda by 8. So what will be your L by 2? That would be lambda by 60. So if you know f theta, then you can put here h phi s, and if e theta s expression you can get to know. Then you can write down P average. Now you need to write down P radiated. So what will be your P radiated? I naught square by 2. What will be the radiation resistance? For lambda by 2, it was 73. For lambda by 4, it was 73 by 2. For lambda by 8, it would be 73 by 4. So it is 73 by 4 under root mu r by epsilon r. What about R radiated? 73 by 4 under root mu r by epsilon r ohm. And what about Z in? Z in will be 73 plus J 42.5 divided by 4. So you need to remember from lambda by 2. Lambda by 2 to lambda by 4 to lambda by 8. Half, half, half. Power radiated will also be half, half, because current will be same. That is coming from the source only. So current will be same. Current will be IRMS square will be same. I naught square by 2. Just the thing will be different in this radiation resistance. And divided by 4 under root mu r by epsilon r ohm. Right. So in one page only we can write down everything about lambda by 8 dipole antenna as well. Well and good. Now let's study about. We need to study about monopole antenna now. Monopole. But before that we need to study about method of image. So let's just say there is a charge q. This is a ground. There is a charge q which is set at the distance d from the ground. At the distance d from the ground, you are having a charge q. Is that clear to you? Okay. Ground means perfect conductor. This is a perfect conductor. Now if I ask you what is the electric field at point P because of this charge q, then what you will write down, sir? Kq by r square. But this is not correct actually. Like this length, let's just say this is r1. So you will say that, sir, it is kq by r1 square. But when we find it out actually, then it is not correct. We don't get this value. So what will happen is that from the ground at distance d plus q charge is there. So inside the ground, you need to assume a hypothetical charge at distance d only, and it has a magnitude. It was plus q and this will be minus q. You need to assume a hypothetical charge of opposite polarity inside the ground, plus q minus q, and at the same distance. This was above d, this is below d. Now at the point P, if you need to find out the total electric field, then that will be coming because of this q as well and because of this minus q as well. So electric field at point P will be because of this q plus q and because of this minus q. But now you will say that, sir, in our college or in our school we have studied that it is always kq by r square. So there they assume that this d is pretty large. This d is pretty large. That means your q charge is there, but it is very much above your conducting plate or above ground. This q charge is there, but this is very much above your conducting plate. So if I ask you at distance r1 at point P, what is your electric field? So you will write down, sir, kq by r1 square. Now this d is very large, right? So inside the ground as well, this will be very far away. This from here to here there is very much distance. So from here to here as well there will be very much distance, because inside the ground you will use minus q. What I need to do here is that because of plus q, I need to find out the electric field at point P. So that will be coming because of plus q, but because of minus q as well it will come. But what we have assumed is that d is very large. So inside the ground as well it will be very far away. So now this distance will be very large. This distance r2, this distance r2, that will be also very large. So actually what will happen is that kq by r square and kq by r1 square ar cap and because of this minus q by r square, r2 square, ar2 cap will also come. But this r2 square is very large, because that is very far away, no? Inside the ground, this d is very far. That means this length will be also very far. So this is very far away. So this r2 will be nearly infinity. So there will be no effect of this r2. Only the effect will be coming from r1, because this r1 is near to this point P. Are you getting this point? I hope you must have understood. Like some people will have a doubt that, sir, till now we used to write down because of plus q, kq by r square. Now, how did you introduce this another thing? So when you used to write down kq by r1 square, then you used to assume that there is no conducting plate, or if there is a conducting plate, or if there is a ground, then your charge is very much above that ground. And your charge is somewhere here. So this d is very large. So you need to take the image. You need to take the image of this charge, that will be minus q below this ground. So because of this minus q, whatever the electric field that is coming, that will be very less. So you don't need to take that in action. So your answer will be kq by r1 square. Are you able to understand this point? Certainly you are able to understand. But as of now, as an EC student, what we need to do? Sir, because of plus q, then I just need to take a mirror image, that would be minus q. That's it. This is what I need to remember. Okay. Let me take a pause. This will be in 32 minutes. So then we will see the mirror image of current carrying wire. Okay. So let me take a pause. Yeah, welcome to the second half of this video. So what we have seen is that we can take the mirror image of plus q as minus q at the same distance above the ground, and at point P you will have the electric field because of this plus q as well, and because of this minus q as well. Now the same kind of analysis you need to do in current carrying wire. So this is a current carrying wire which has the current in this direction, and this is the current carrying wire which has the current in upward direction. So this I can call as vertical wire, this I can call as horizontal wire, right? So in a wire, if the current is flowing in this manner, let's just say this is your 3 ohm and here the current is flowing, that is 3 ampere. So the current is flowing 3 ampere in this manner. So what is the total voltage drop here? 9 volt. So can I assume something like this, that here you are having plus 5 volt and here you are having minus 4 volt, right? But that means here you are having positive charge, here you are having negative charge. Across the resistance, here you are having positive, here you are having negative. That means the current will be flowing in this direction. So if here the current is flowing in this direction, that means can I assume plus q here and minus q here? And if the current is flowing upward, then can I assume plus q here and minus q here? Or how you can say is that always, or forget about this, this analogy is fine. This analogy is fine, right? So you can assume plus q here, minus q here, plus q here, minus q here. Is that clear to you? Right? So now if I need to take the image, so what will be the image of plus q? That would be minus q somewhere here. And what will be the image of this minus q? That would be plus q somewhere here. So now if I need to make a wire, I need to take an image of wire actually. But what I am doing is that I took the image of plus q and I took the image of minus q, because this is what we studied. Image of plus q is minus q. So image of minus q will be plus q. So this is what we studied. So here where will be the current flowing? In the opposite direction, in this direction, right? So if I copy this current inside the ground, then the direction will be opposite. Are you getting this point? What about this one? So how will you take the image? Minus q. What about this image? Plus q. That was about distance d. So this is also below distance d. If this is about distance d1, so this is also below distance d1, right? So I took the image of plus q and minus q. So what is happening here? I should have used a different color of pen. So what is happening here is that if I assume this wire, I am taking the mirror image of this wire only, but I need to know the direction of current. So what will be the direction of current? From plus q to minus q. So in case of horizontal wire, the direction of current got changed. It got opposite. But in case of vertical wire, the direction is same. Let's just say this is your ground. So here this is the current. So downward as well, the same current is there. But this is your wire. If this is the current, then downward the current is opposite. Are you getting this point? Now let's assume, and now I hope you are understanding why we are studying this concept. Because what we need to study monopole antennas. So for monopole antenna, what will happen is that we will have some this kind of wire, right? Some this kind of wire. So that will be placed above the ground. So if I need to take the mirror image in the wire, I am assuming the current is flowing like this. In any direction current can flow, but I am assuming the current is flowing like this. So how will I take the mirror image? I will take mirror image of the horizontal wire and I will take the mirror image of the vertical wire. In the horizontal wire, the direction will be, if this is the direction, then here this will be the direction. If this is vertical, then this is the vertical. So in this manner here the current is flowing, and here in this manner the current is flowing, and in between there will be supply. So a complete path of current is there, right? So let's start studying about our monopole antenna. So first we are going to study about quarter wave monopole antenna. So if this is written quarter wave monopole antenna, that means height of the monopole antenna is lambda by 4. This height is lambda by 4. So this is your actual antenna that is given to you. This is the actual antenna that is given to you. Now what I will do is that I know that if it is placed just above the ground, if it is center fed, that means what I can do, I can take its mirror image, and that mirror image will be something like this. And I can see the direction of current as well. If this is the direction of current, then here this will be the direction of current. So I can take the mirror image. So now what it feels like? It feels like it was a monopole antenna of quarter wave, but now it is becoming a dipole antenna of half wave. Here the length was lambda by 4, but now this length will also be there, no? Although this is hypothetical, this is not actually there. But if I ask you, at point P, electric field will be coming because of this current, electric field and magnetic field will be coming because of this current and voltage, and also because of this current and voltage. Is that statement true? Yes. Because here what did we saw? At point P, the electric field is there because of this Q and minus Q. Now in this case, at point P, the electric field and magnetic field will be there because of this current and voltage, and because of this current and voltage as well. Although it is hypothetical, but still it will affect the electric field and magnetic field at point P. And if it is affecting electric field and magnetic field, that means what it will do? It will affect your P average as well, right? So all these things we need to see now. So it is acting like a half wave dipole antenna, right? But it is not actually half wave dipole antenna, because this part is actually not there. So a few things will be changing, and for this antenna, for this monopole antenna, what is the value of theta? This is the most important point here. What is the range of theta? From 0 to pi by 2. But when we find out all these things, let's just say in my half wave dipole antenna, I found out all these things, power radiated. So what did I take in action? I took in action is that my R is going from 0 to infinity, my theta is going from 0 to pi, and my phi is going from 0 to 2 pi. Because here it was complete antenna was there, right? Same goes for this quarter wave dipole antenna as well. If I am saying dipole, that means my theta is certainly going from 0 to pi. 0 will also be included, pi will also be included. And what about phi? Phi is this circular way, like phi is the circular way, like this will be your phi, no? But I am talking about the angle from z axis. So here angle from z axis will be completely from 0 to 180. But here the angle from z axis, this is your angle from z axis, that is your theta. So that can be, what will be the range of that theta? Like you cannot see it properly. So this angle theta, this can be from 0 to pi only, because that is hypothetical, no? This is not actually there, that is hypothetical. So it will be there from 0 to pi only. Are you getting this point or not? Right? Well and good. Okay. So now we need to write down E theta s, E phi s, all these things we need to write down. Okay. So what will be our F theta here? F theta, that would be cos beta L n by 2 I am writing. Why L n by 2? Because new. Because where F theta will be used? F theta will be used in E theta s and H phi s. What will be your E theta s? That will be J I naught upon 2 pi r, J neta I naught upon 2 pi r, sorry. J neta I naught upon 2 pi r, J neta I naught upon 2 pi r, F theta a to the power minus J beta r A r cap, A theta cap. And here also it will be used. Let's not write it down, whatever it is. Okay. So here also F theta will be used. So F theta will be used in electric field and magnetic field, and the electric field and magnetic field will be there because of all the component, because of this wire as well and because of this wire as well. Electric field and magnetic field at point P will be there because of this wire as well and this wire as well. So if the complete circuit is coming into action, if this complete antenna is coming into action, so it is like a lambda by 2 antenna, no? So L nu is your lambda by 2. Are you getting this point or not? Your length is lambda by 4, but if you are writing down the expression of E theta s and H phi s, that means you are writing because of lambda by 2. Is that clear to you or not? So now you are gonna treat it as a lambda by 2 dipole antenna only, or you can say half wave dipole antenna only, although it is quarter wave monopole antenna. But we got to know that we need to take mirror image. If we are taking the mirror image, that means it is working as a half wave dipole antenna only. So all these things we need to write down: cos beta L by 2 cos theta minus cos beta L nu by 2 divided by sin theta. So what is your f theta here? F theta is cos pi by 2 cos theta. You can put the value. L nu you will put at lambda by 2, so it will be lambda by 4. So cos pi by 2 cos theta divided by sin theta. That f theta you can put here and you will get the expression of E theta s and H phi s. So it will be same as E theta s and H phi s. It is same as your half wave dipole antenna. So here what I have written, H phi s of monopole lambda by 4 is same as H phi s of dipole lambda by 2. Say yes or no. Do you agree to this point? E theta s of monopole lambda by 4. This is the expression we are writing E theta s for monopole lambda by 4, but we got to know that it is working as a dipole lambda by 2. This is monopole lambda by 4, but it is working as dipole lambda by 2. So E theta s is same as H phi s is same as H phi s for monopole lambda by 4 is same as H phi s dipole lambda by 2. So similar goes here. E theta s for monopole lambda by 4 is same as E theta s dipole lambda by 4. Sorry, dipole lambda by 2. Not 4, sorry, lambda by 2, because length is becoming, this is also lambda by 4 length. So total new length is becoming lambda by 2. What about P average? What do you think? What is P average? What is the simple formula of P average? That is ES cross HS. So what you are writing? P average for monopole lambda by 4. P average for monopole lambda by 4. So if P average for monopole lambda by 4 will be same as what? P average for dipole lambda by 4. Again I am saying it wrong. P average for monopole lambda by 4 will be same as P average dipole lambda by 2. Why is that so? Because your E theta expression for monopole lambda by 4 is same as E theta expression dipole lambda by 2. Your H phi expression for monopole lambda by 4 is same as your H phi expression dipole lambda by 2. So this expression for monopole lambda by 4 or dipole lambda by 2 both are same. This expression for monopole lambda by 4 or dipole lambda by 2 both are same. That means certainly your P average for monopole lambda by 4 will be same as P average dipole lambda by 2. Do you agree to this point? You are given a monopole antenna of lambda by 4. You will get to know that, sir, it will become lambda by 2. Okay, it is becoming lambda by 2. So electric field will be there because of the complete lambda by 2. Magnetic field will also be there because of complete lambda by 2. So expression I will get D2 same. E theta and H phi expression I will get D2 same. P average expression also I will get D2 same. Why is that so? Because if E theta and H phi are same, that means P average will also be same. But what about P radiated? Think about it. What you do for finding P radiated? P average dot ds. Now you will think that, sir, P average is same for monopole lambda by 4 and dipole lambda by 2. P average is same. Sir, ds is also same. So sir, this power should also be same. No. Limit. What is the limit of phi here? 0 to 2 pi. What is the limit of theta here? 0 to pi by 2. So if limit is half, in the previous case, if you write down P radiated, let's take it downward. If I write down P radiated for dipole lambda by 4, sorry, dipole lambda by 2, not lambda by 4. if I write down P radiated for dipole lambda by 2, so what I will write down? P average, here I am writing lambda by 2. This is your P average mono lambda by 4 dot ds. Now you will say that, sir, this guy and this guy are same, but what about the limit? Here the limit was, but here the limit is 0 to pi, but here the limit is 0 to pi by 2. So important, very important to mark this thing. The limit is half here. So whatever the power you get here, that will be double of this power, no? Because limit is half. And practically also you can think, this is your lambda by 2 dipole. This is your lambda by 2 dipole. So how it will radiate the power? In this manner, in this manner, in this manner, in this manner, here, 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 here. Completely it will radiate like this. But what about your lambda by 4? This is the ground here. Now what did you say? This is your monopole lambda by 4. Monopole lambda by 4. Then you said that, sir, I will take the mirror image, so it is becoming lambda by 2. So now where it can radiate the power? Here, 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 here. This guy could have radiated the power downward as well. But can this guy radiate the power downward? No. Because here there is perfect conductor. So now it cannot radiate the power downward. So if this was radiating the power in full circle, this was radiating the power in full circle. So let us say if this was radiating power x, then now this is radiating the power in, I should not say full circle, it is a sphere. This was radiating the power in full sphere because it will be radiating the power in 3D. So this is a full sphere, but this is a half sphere only, no? So what, if this is radiating x power, then how much power this will be radiating? X by 2. So when we used monopole antenna, monopole lambda by 4 antenna, so we were getting same results as dipole lambda by 2. So using smaller length as well, I am getting the same results, but same results of E theta, H phi and P average. But my P radiated did not get double. Are you getting this point? So what I am going to write down here is that my P radiated did not get double. If I want more electric field, if I want more magnetic field, then that is a good idea that I use lambda by 4 monopole antenna I can use. If I want more electric field and if I want more magnetic field, then I can use monopole antenna of lambda by 4 length. But if I want more power radiated, then I need to use lambda by 2 only. Are you getting this point? So what this will be? This will be your half P radiated of dipole lambda by 2. So power is half. Is it equals to P radiated dipole lambda by 4? Yes. Dipole lambda by 2. What was the power radiated? This. Dipole lambda by 2. What was the power radiated? This was the power radiated. Now dipole lambda by 4. What is the power radiated? This is the power radiated. So dipole lambda by 4, the power radiated is half of, here if I write down power radiated, here I did not write down the limit of phi. Phi was going from 0 to 2 pi and r was going from 0 to infinity. Now here if I write down the power radiated of dipole lambda by 4 is half of power radiated by dipole lambda by 2. Is that correct? Certainly it is correct, because radiation resistance is half. If radiation resistance is half, that means power radiated is also half. So let's just say I give you a lambda by 4 antenna. I am giving you a lambda by 4 dipole antenna, and I say, what did I give you? I give you this lambda by 4 dipole antenna. Lambda by 4 dipole antenna. This complete length is lambda by 4. This I am giving. Okay. And on the other hand, I am giving you a monopole antenna of lambda by 4. Then I say that I need power radiated equals to the dipole lambda by 2. What did I say? I need power radiated same as dipole lambda by 2. So can you give me that power? No. Because you will say that, sir, this power and because of this power, both power will be same. But sir, if you need electric field and magnetic field equal to the dipole lambda by 2, then sir I can use this one, because this will give me the electric field and magnetic field equals to that dipole lambda by 2, because we can use the mirror image, so it will give me the same electric field and magnetic field. It will give me the same P average as well. But when I find the P radiated, so whether you take dipole lambda by 2, sorry, whether you take dipole lambda by 4 or you take monopole lambda by 4, both are same thing, because both will give me the half power of dipole lambda by 2. Are you getting this point? So in the examination, if monopole, quarter wave monopole is coming, so in the mind picture should be clear to you. Okay, this is lambda by 4, but this is above the ground, so it will be lambda by 2. So E field, H field, everything will be same, but power radiated will be half. That's it. So when quarter wave monopole is coming, I will treat this as half wave dipole, but I will always keep in mind that power will be half. That's it. If I need to do this calculation, if I need to do this calculation, if I need to do this calculation, then blindly I will treat that as dipole lambda by 2. But if I need to do this calculation, then I will treat this as dipole lambda by 2, but eventually I will write down my answer as half. Is that clear to you? Okay. So let's see the next question. I guess there is a question only. Okay, it is not given. Here I have written just the final statement, which is this, that P radiated monopole lambda by 4 is equals to P radiated dipole lambda by 2. Okay, and I don't need to prove it. This I have already proven. So very important point, that why we are using monopole antenna. We are using monopole antenna so that we can get the same H theta s, sorry, same H phi s and E theta s and P average as the double of dipole antenna. Let's just say I am using lambda by 4 monopole, so I can get these results of lambda by 2 dipole. I am using lambda by 4 monopole, so I can get the same results as lambda by 2 dipole, but I will never get power radiated double. No, power radiated will be half of this one. Are you able to understand this point? So you don't need to mug up all these things. Whenever the question is coming quarter wave monopole, you will treat this as half wave dipole, and in the back of the mind you will always know that power radiated will be half, rest all calculation will be same. Is that clear to you or not? Say yes or no, right? So now you write down all the R radiated values. What was the R radiated for half wave dipole? 73 under root mu r by epsilon r. Yes. Can you write down R radiated for this one? R radiated for this one. What is this? I naught square by 2 R radiated monopole lambda by 4. What this will be? I naught square by 2 into R radiated dipole lambda by 2, and then there is by 2 as well. So this is getting cancelled, this is getting cancelled. So what is your R radiated monopole lambda by 4? That will be equals to R radiated dipole lambda by 2 divided by 2, or you can say it is equals to R radiated of dipole lambda by 4. Say yes or no? And that is pretty obvious, because if the power is half, that means radiation resistance is half. So let's complete this table. So if here the radiation resistance is 73, then what was about quarter wave dipole? 73 by 2 under root mu r by epsilon r rho. Quarter wave monopole, quarter wave dipole and quarter wave monopole will have the same power radiated. Why is that so? Because quarter wave monopole acts as half wave dipole for E theta s, H phi s and P average, but for P radiated it is half only, and same goes for quarter wave dipole as well. So this will be the same, right? For lambda by 8 dipole, so what you need to do, half of this one you can say, or 1/4 of this one you can say, right? Under root Hertzian dipole, pi square under root mu r epsilon r will also come. Now we studied about lambda by 2, lambda by 4, lambda by 8. All these were greater than lambda by 10. we have studied about length greater than lambda by 10. We have studied about length less than lambda by 50 as well, because this was your Hertzian and this was your half wave, quarter wave, lambda by 8, all these things were there. Monopole, dipole, everything we studied. So this Hertzian we have studied and this we have studied. What about the length between lambda by 10 to lambda by 50? What about that? So we do not usually study it until now in the gate examination. In the history of gate examination in 2006, I guess, there was one question from this. And that was also very like, what do we say? That, and there also the answer was not that clear. So there is very, very rare chance that this would be coming. Very, very rare chance that they will ask anything from here. If they ask, maximum they can ask R related. So for that I will write you down a formula that you can apply. So maximum they can ask R related from this much range. We have studied about all these, but we did not study about this range. These are also known as linear dipole antenna only, but the length range will be this. So length will be mentioned in the question. So you can check that out from there. But there is very rare chance that any question will be coming from here. Are you getting this point? So if they ask you R related, mostly what they can ask you P related or R related. So if you know R related, then certainly you can write down P related, because what is your P related? I naught square by 2 into R related. So what will be R related for this length? Same as this, 80 pi square, length, here I am writing length by lambda square. Why I am writing DL here? Because this is very small. Now this is not very small, so that's why I am writing L under root mu r by epsilon r. Then sir, what is the difference? This is same as Hertzian dipole. The difference is 2 will come here. That's it. So let's just say if they are asking me for lambda by 20. For lambda by 20, they are asking me the radiation resistance. So what I am going to do? Sir, 80 pi square into what is the length? Lambda by 20 divided by lambda. 2 also I will multiply here into 2 and then mu r by epsilon whatever that is there. So what I will be getting with 80 pi square divided by, this is 40 into 40, right? Here there was lambda by 40, this would be lambda by 40 divided by lambda. So what is this 2? Length is lambda by 20, then another 2 is there. So this is lambda by 40. So 40 into 40, lambda is getting cancelled. Yeah, this is what I am getting. So what will be my answer? Pi square by 20. So this will be the answer, which they will rarely ask. But if they ask, you should know the formula, that it is same as the Hertzian dipole, but whatever the length is given, I need to take half of that length. Whatever the length is given, I need to take half of that length. Now let's just say they have given lambda by 20 monopole, lambda by 20 monopole antenna. Then how will you solve it? I am giving you the question. For lambda by 20 monopole antenna, you need to find out P radiated or R radiated. How will you find out? The question is lambda by 20 monopole. So that will be same as lambda by 20 dipole. Or what you can think, that sir, lambda by 20 monopole is there. That means if I take the double, it will act as lambda by 10 dipole. But for P radiated, it will be half of that. Or you can say for R radiated, it will be half of that. So now I need to find out lambda by 10 dipole. For lambda by 10 dipole, what will be my R radiated? So that would be 80 pi square into lambda by 10. Lambda by 10 will be taken in this range only. Okay. So that would be lambda by 10. So 1 by 20 square. So 80 pi square into 20 into 20. So whatever you are getting, pi square by 5. But again, this you have found out for lambda by 10 dipole. But when you find it out from lambda by 10 dipole, if you need to go to lambda by 20 monopole, that means you need to make it half. Because this will act as this for A theta, H phi and P average. But for R radiated, it will be half of that. So your answer will be pi square by 10. Are you getting this point? So this will be the answer. So in that manner, we need to solve. These kind of questions can be asked in the examination, but very rare. Yeah, okay then, all clear. So this is what we have studied. We have studied about radiation resistance, and what did I tell you? These are the more important ones. These are the important ones. They can ask you for half wave, quarter wave dipole, quarter wave monopole. They can ask you for half wave monopole as well. They can ask these kind of questions. Lambda by 8 length dipole, these they can ask. Mostly if they are asking question on radiation resistance, then it will be coming from here only, from these 5 only. Is that okay for you? Then this range will not come, lambda by 10 to lambda by 50. Even if it is comes, then we have the aptitude that we can apply this formula and we will be able to get our answer. Whether they are asking for monopole or dipole, we will be able to get this answer. This we have written for dipole. So this formula we have written for dipole, not for monopole. This formula has been written for dipole. If they are asking for monopole, then accordingly we can adjust and we can get our answer, right? So this we have seen. Now we need to see some questions. So this is one of the questions that I framed only, very easy it is. And then these are two questions from Sadiku. So these questions we need to solve from Sadiku. Well and good. So first see this one, power radiated by quarter wave dipole antenna is x watt. Find the power radiated by quarter wave monopole. So just now we have seen that they are equal. So x watt will be the answer. But in the examination, this is not what you think. What you will think, okay, what they are asking, quarter wave monopole. So quarter wave monopole will be same as half wave dipole. Quarter wave monopole is same as half wave dipole, but not in case of power radiated. So power radiated will be half of dipole of lambda by 2, and that is equals to power radiated of dipole but lambda by 4, because dipole lambda by 2 will have 2x power, then dipole lambda by 4 will have x power. So what is the answer? Here we are talking about mono lambda by 4. So what is the answer? X watt, which is very simple, which we have already seen and we have done that enough discussion. But I am telling here what you will think in the examination. Let us say if I had asked you the E theta expression, E theta s expression, or if I asked you the magnetic field expression, or if I had asked you the P average expression. So at that time what you would be thinking? You would be thinking about dipole lambda by 2. But if I am asking P radiated, so at that time you need to think that power will be half. That's it. Okay. So now this is the question. A magnetic field strength is given. Okay, it is required at a point at theta equals to pi by 2, 2 kilometer 2 kilometer from an antenna in the air, neglecting ohmic laws. What is this ohmic laws? That we will study. Okay, don't worry about this. That what do you mean by this ohmic laws? That we are going to study later on. So rest all terms you know, magnetic field you know, theta you know, 2 kilometer you know. How much power must antenna transmit if it is a Hertzian dipole? So let's start solving with the first one. First is the Hertzian dipole. So power, how much power it should transmit? So P radiated they are asking. So first question, for Hertzian dipole, what is P radiated? P radiated is 80 pi square dl by lambda whole square, under root mu r epsilon r will be 1. So here I told you that length should be less than lambda by 50, but here they have given lambda by 25 length. So this is given in Sadiku, that's why I framed this question, but it should be less than lambda by 50. But lambda by 20 is certainly greater than lambda by 50. But again, if they have given Hertzian dipole, so I will use this formula only. That they have written the name Hertzian dipole. Actually, it should be less than lambda by 50. It could be lambda by 75. It could be lambda by 60. It could be anything. But they have given lambda by 25, which is a bit it should be a bit controversial. But again, we need to take a Hertzian dipole only. So this is what we need to find. And power radiated they are asking. So this is the radiation resistance. So I naught square by 2. So for power radiation, I have the value of lambda. I have the value of d. I don't have the value of lambda, but I have the value of dl. So dl by lambda I need. I don't have the value of I naught. So now I need to find I naught. Then I can find out P radiated. So this is how we should proceed in the question of antenna. That always first write down what they want to ask. They want to ask P radiated. Now for P radiated, what I need? I naught. So now my target should be to find I naught value. So what I am having? I am having magnetic field strength. So H phi s I am having, but only the magnitude I am having, no direction, nothing like that. That is 5 micro ampere per meter. That is given. And theta value is also mentioned. That is pi by 2. And R value is also mentioned. That is 2 kilometer. Okay. So do you know H phi s expression for Hertzian dipole? For Hertzian dipole we are solving. So that is ideal sin theta upon 4 pi r e to the power minus j beta r, that is phasor, that will not come because we are writing the magnitude. Then j beta is there, right? So j will also come because that is also a phase. So only beta would come here. Only beta would come. And direction will also not come. So what is beta? Beta is 2 pi by lambda. So beta is 2 pi by lambda. So did you understand how did I write it down? Yes. So what I am gonna do? I naught I need to find. dl is lambda by 25 into 4 pi into 2 pi, that will be 2 only, and here there is r which is 2 kilometer, and here there is lambda as well. 2 pi and 2 pi, this has become 2, r is 2 kilometer, this is lambda, and sin pi by 2 is 1. Sin pi by 2 is 1. Well and good. Yeah, that's it. So lambda is also getting cancelled, and that is equals to 5 micro. So just value you need to put, nothing else. So from here, what is the value of I naught you are getting? So I have the calculator. No need of calculator, because 100 it is 110 to the power 5. So this should be 0.5 ampere. So I naught value is 0.5 ampere. So this is the value of I naught we are getting, but for Hertzian dipole, we are getting this. So I naught value is 0.5 ampere. Now I can put here. So what will be my P radiated now? P radiated will be 80 pi square into dl. dl is lambda by 25. So lambda by 25, lambda by 25 divided by lambda whole square into I naught square, that is 1 by 2 square divided by 2. I naught square by 2. Okay, then let's solve it now. 80 into pi divided by 25 divided by 25 divided by 8. So 0.1579. Yeah. So we are getting 157.9 milliwatt. So this is the answer of first one. P radiated. That is the answer of first one. Let's go with the second one. B. What B is saying? Again I need to find P radiated. But for which one? I need to find P radiated for half wave dipole. So what is the formula for that? I naught square by 2 into 73. Under root mu r epsilon r is 1 only, because since this is air. Why this is air? Because antenna is in air. Well and good. Yeah. So I naught value I need to find now. So for that, what I have? H phi s expression I have. What that would be? J I naught upon 2 pi r, J will be gone. J I naught upon 2 pi r, and f theta, then e to the power minus j beta r, that will be gone. Nothing will be there, then direction will also be gone. So this is the magnitude. But let's talk about f theta now. So for half wave dipole, what it is? Cos pi by 2 cos theta divided by sin theta. But what is the value of theta? Theta is 90 degree. So here I need to put 90 degree. Cos 90 and sin 90 degree. Sin 90 is 1. Cos 90 is 0. Cos 0 is also 1. This is also 1. So this will be 1 only. So f theta value is 1 only. So I naught upon 2 pi r. 2 pi r is 2 kilometer. That is equals to 5 micro. That is 5 into 10 to the power minus 3. Sorry, 10 to the power minus 6. 5 micro. So from here I need to find the value of I naught. So that would be, this will become 10 to the power minus 2. So 2 pi into 10 to the power minus 2. 2 into pi, 2 pi into 10 to the power minus 2. So 62.8 milliampere, right? To the power 4, 10 to the power minus 2. 6.28 into 10 to the power minus 2. 62.8 milliampere. Yeah, this is your I naught. But what I need to find? P radiated I need to find. What that would be? 62.8 whole square divided by 2 into 73. Milli got whole square. So what you are getting here? Microwatt. So this will be in microwatt, because 62.8 milliampere, right? So if I solve this, what I get? Wait a second, it is 62.8 milliampere only, no 10 to the power 10 to the power minus 2. 6.8. Yeah, okay. So 62.8 whole square divided by 2 into 73. But this is in micro, but if I need to take in milli, then it would be 143.95 milliampere. Right, this is what I'm getting. Yeah, 143.95. 143.95 milliwatt. This will be the answer. You need to do the calculation, nothing else. Let's see the C. For C, what they are asking. Again, for now, this is quarter wave monopole. Okay, quarter wave monopole. What will be the answer? Half. Half wave dipole radiates x power, so quarter wave monopole will radiate half power. So what will be the answer for C? So P radiated will be whatever that is there, 143.95 divided by 2. Divided by 2. So 71.97 milliwatt. Well and good, very easy, very straightforward, right? Okay, then let's move to the next one. Electric field strength of 10 microvolt per meter is to be measured at an observation point theta equals to pi by 2, 500 kilometer from a half wave dipole antenna operating at this. What is the length of dipole? First question. Length I need to find. Length is given, no, it is half wave dipole. Length is equals to lambda by 2. Now I need to find the value of lambda. So for lambda, what I have the electric field strength E theta s I am having, which is equals to 10 micro volt per meter. I have theta value, I have R value 500 kilometer. I also have F value 50 megahertz. And somewhere it should be mentioned that it is in air. But if it is not mentioned, we will assume air only. So what is lambda? Lambda is equals to Vp by F. But here Vp will be C, 3 into 10 to the power 8, because it is not mentioned which medium is that. And divided by 5 into 10 to the power 7. So that would be 6 meter. So lambda is 6 meter. So what is the length? Length is 6 by 2, that is 3 meter. So this is the length. This is the answer of first one. Very straightforward. Calculate the current that must be fed to the antenna. So lambda by 2 antenna is that. So what will be the E theta expression? So that's why I told you that again and again we will be using this expression. No? So you will be remembering it. So what will be the E theta expression? Because I need to find the current. So for that I can do this thing, right? Because E theta is expression I can use. Because what that would be? Neta I naught upon 2 pi r. There is high chance that you will forget this neta. So don't forget this neta. In the previous case, H5 expression was given, right? H5 expression was given, so no neta was there. So, but generally when we write E theta, we forget this neta. So don't forget that. Into F theta. A to the power minus j beta r will be there, that will be of no use. AR cap will also be of no use. So what about F theta now? So F theta for half wave dipole. Half wave dipole. That we already remember, or we can derive as well. But only this will be used. Many times only this will be used. And what is the value of theta they have given? Theta they have given as pi by 2. So again this will become 1 only, because cos pi is 0. Cos pi by 2 is 0, so this will become 1 only. So that is your neta is 120 pi into I naught divided by 2 pi into r. R is 5 into 10 to the power 5. 5 into 10 to the power 5, which is equals to 10 micro. 10 micro means 10 to the power minus 5 only, right? This is your 10 micro, that means it is 10 to the power minus 5 volt per meter. So what you are gonna get? 60, 5 by 60. I note is coming out to be 5 by 60, and this is what they asked. They asked that current only 5 by 60. So I note is 5 by 60 ampere, or what could be the answer? 5 by 60 is 0.83.33. 83.33 milliampere. Let's just be sure with the answer. Is the answer correct? 83.33 only. Next, what they are saying? Power radiated. Calculate the average power radiated by the antenna. P radiated. That would be I naught square by 2 into R radiated. R radiated I already know. that is 73 ohm, that is 83.333 whole square divided by 2 into 73 into, since this is milli, so now it will become microwatt. Square by 2 into 73. So 253.47. 253.47 milliwatt. This is the power radiated we are getting. Actually, this should have been solved by you. Like you could have solved this very easily. Is that correct as well? 253.5. Yeah. Now this is a good question. If a transmission line of Z naught equals to 75 ohm is connected to the antenna, determine the standing wave ratio. So what I'm gonna do is that this is my D. So there is very high chance that you will get something wrong here. Transmission line is connected to the antenna. So this transmission line is having Z naught of 75 ohm, right? This transmission line is having Z naught of 75 ohm. What you need? You need standing wave ratio. What is that? 1 plus gamma L divided 1 plus mode of gamma divided by 1 minus mode of gamma. So can I find gamma here? Yes. What will be gamma? This load ZL minus Z naught upon ZL plus Z naught. So what value ZL I will put? This is my ZL, no? This is my ZL. This is my ZL. So what will be the value of ZL here? 73 ohm. No. ZL value will not be 73 ohm. 73 plus J 42.5. That's the error which happens with a lot of students. You take 73 ohm for radiation resistance, but when you take the complete impedance of your antenna, you need to consider the reactive part as well. So a lot of times students forget this. They forget the reactive part. So always take that in action. Whenever I am finding reflection coefficient, I will take the reactive part as well. Never ever forget it. Okay. So 73 plus J 42.5 minus 75 divided by 73 plus J 42.5 plus 75. So these kind of calculation we have done a lot of times. Step by step calculation I have done. Like first I will take the magnitude of the upper half, then I will take the magnitude of lower half, then I will calculate the angle as well. So step by step calculation I have already shown in transmission line. So here I am going to directly write down the answer. What is the mode of gamma I need? I don't need the angle. So mode of gamma is coming out to be 0.2763. Okay, mode of gamma is 0.2763. So what will be the standing wave ratio? That would be 1 plus 0.2763 divided by 1 minus 0.2763. So when I solve it, I get 1.763. Just the calculation part is there. This was easy question only, but this is something that we forget. If you only take 73, then the answer will be wrong. Is that clear to you? All good? So that's it about our linear dipole antenna as well. Now we need to study about not standing wave pattern, we need to study about radiation pattern. Radiation pattern we need to study. So first we will see normalized electric field, then we will see what is the normalized electric field, then we will plot it with respect to theta, with respect to phi, and for different kind of sense we are going to do it. For lambda by 2, for lambda by 4, for monopole, for dipole, for full wave as well, for lambda length as well, for 3 lambda by 2 length as well, for 1.25 lambda length as well. We will find out the position of nulls as well. So all these things we are going to do. And there I told you that what is the meaning of first null bandwidth, right? In the last lecture I told you that not bandwidth, again and again I am saying bandwidth. First null beamwidth, it is beamwidth. So what is the meaning of first null beamwidth? So that also I need to tell. What is the meaning of first there? Why I used to call that first? So that also I will tell here. So certainly I will take a break, but let's solve a question on mathematics. Cos A is equals to cos B. So you need to find the relation between A and B, and then you need to find the all possible value of theta for this particular relation, because this will be used in our radiation pattern. So first we need to solve this mathematics. So what do you think, what will be the relation? Cos A is equals to cos B. So let's just say let A is 0 degree. Let A is 0 degree. That means cos 0 degree is equals to cos B. So cos B is equals to 1. And what is the graph of cos? What is the graph of cos? The graph of cos is like this. Right. So now cos b is 1. So what all values you can have? 0 degree, b can be 0 degree. I am writing in radian now. B can be 0. It can be 2 pi as well. It can be again 4 pi, because after 2 pi every value will be repeated. 4 pi, 6 pi, in the same manner. But it could be negative as well, no? 0. It could be minus 2 pi as well. What is, sorry. What is this point? What is this point? This point is minus 2 pi. What is this point? This point is 2 pi. So similarly, it could be negative as well, no? 0 plus minus 2 pi plus minus 4 pi plus minus 6 pi. So if a is 0, b can be these values. Let's take more example. This was example 1. Let's take more example. Let a is equals to, let's take pi. A is equals to pi. Or let's take a equals to pi by 2. Any value you can put. This is your a equals to pi by 2. So if I take a equals to pi by 2, then what I will get? Cos b is equals to cos pi by 2. And what is that? Cos pi by 2 is 0. So cos b should be equals to 0. So from there, what is the value of b you are getting? Pi by 2. 0 will not be that satisfying, because in 0 will be repeated after pi. So forget about that. Let's not take that value, because it will create needless confusion. So let's take a equals to pi only. So what you are getting? Minus 1. So cos b is equals to minus 1. So where you can get cos b equals to minus 1? So this is here you are getting minus 1 at pi. At pi you are getting minus 1. Then after 2 pi it will be repeated. So at 3 pi as well you can get minus 1, because it will be repeated after 2 pi. So at 3 pi as well you can get minus 1. At 5 pi as well you can get minus 1. At 7 pi as well you can get minus 1. But same thing can be repeated at minus pi as well, no? Cos b equals to minus 1 can be at a minus pi as well, at plus pi as well, at plus minus 3 pi, at plus minus 5 pi, plus minus 7 pi, because it is symmetric, no? Whatever that is here, the same thing is happening here as well. So this is the value of b. For if a is pi, then this is my b. If a is 0, then this is my b. So can I write down my a is equals to plus minus b plus minus 2n pi? Say yes or no. If this is the relation cos a equals to cos b, then a is equals to plus minus b plus minus 2n pi. You can verify it here. If a is 0, or you can write down otherwise as well. You can write down b is equals to plus minus a plus minus 2n pi. Both things can be written. Anything can be written. So we can verify from here. If a is 0 degree, then b is plus minus 2n pi. If a is 0, then b is plus minus 2n pi. Are we getting the same thing? You can start. Value of n is 0, then 0. Value of n is 1, 2 pi. Value of n is 2, 4 pi. Value of n is 3, 6 pi. Right? But the value of n is going from 0, 1, 2 till infinity. So this thing should also be there. So cos a equals to cos b, then you can write down that a is equals to plus minus b plus minus 2n pi. Here we have proved it. You can write down other thing as well. That if this plus, if this b goes here and a comes here, the same answer you are getting. Or this plus minus 2n pi goes here, then the same thing will be there. So both of the things you can write down. Is that clear to you or not? You can check for a equals to pi as well. If a is equals to pi, then what you are getting? B equals to plus minus pi plus minus 2n pi. Then you can see the answers. You are getting the same answer. If you take n equals to 0, you are getting plus minus pi. If you take n equals to 1, you are getting plus minus pi plus plus minus 2 pi. That means plus minus 3 pi. In the same manner, you can proceed. Say yes or no. All good? That's all this question. And we will not use this formula. We will rarely use this formula. Without even using this formula, we will be able to get the answer. So let's check that question. That cos something is equals to cos something. So what I can write down? That 1.25 cos theta is equals to 1.25 plus minus 2n pi. And here also plus minus. Just a second, just wait a second. Yeah, so I am back now. So what we are doing, we just equated it, and then what we need to do, pi, pi and pi, these are getting cancelled, and cos theta is equals to, can I divide it? Yeah, plus minus 1 plus minus 2n by 1.5, 1.25, right? So what is the value of cos theta you are getting? Cos theta is equals to plus minus 1, 2 by 1.25. 2 by 1.25 is 1.6 n. Now values of n we need to take. So if value of n is 0, then cos theta is equals to plus minus 1. And if cos theta is equals to plus minus 1, that means theta is can be, if cos theta is equals to 1, that means theta is 0 degree. And if cos theta is equals to minus 1, then theta is equals to pi. Now you will say that, sir, cos theta equals to plus 1. Cos theta equals to plus 1, then theta could be 0 degree or 2 pi or 4 pi. All these can also be possible, no? But in our question, when we study radiation pattern, here also I should write down that theta is, in the question also it would be mentioned that theta is from 0 to pi only. Okay, theta is from 0 to pi. It should be mentioned in the question. Why I am mentioning this thing in the question? Because I know that in radiation pattern, my theta will go from 0 to pi only. Because in spherical coordinate system, my theta can go from 0 to pi only. So I will write down only those values which is in this range from 0 to pi. Okay, so this is mentioned in the question. Now value of n you can pick. So from here you go to know that cos theta is equals to plus minus 1. You understood, no? Cos theta can be plus 1, cos theta can be minus 1. If it is plus 1, then 0 degree. If it is minus 1, then pi. What about this one, next one? So I am getting plus minus 1.6. So from here I can get 4 results. That my cos theta can be equals to, both plus I am taking, plus 1 plus 1.6. What that would be? 2.6. My cos theta can be equals to, first one plus I am taking, next I am taking negative, minus 0.6. My cos theta could be equals to, first I am taking as negative, second as plus, so 0.6, and last I am taking as first one as negative, second one as also negative, so cos theta equals to minus 2.6. But you know that cos theta ranges from minus 1 to 1, so this is not possible, this is not possible. So from here as well we can get two answers. The cos theta equals to plus 0.6 and cos theta equals to minus 0.6. So always I prefer, whenever I solve trigonometric function, I always prefer making the graph. So I don't trust on my calculator. What people will do that, sir, 0.6 cos inverse. But it's good to trust on your calculator, but always make the graph as well. So this is my pi. So now for cos theta equals to minus 0.6, that would be greater than pi by 2 and less than pi. So it would be somewhere here. Cos theta equals to minus 0.6. And what about plus 0.6? It would be somewhere here. So now if I ask my calculator 0.6 plus minus cos inverse. So this is giving me 126.86 degree. So now I am happy that, yeah, less than 180 and greater than 90. So it is giving me 126.86 degree. And if I ask 0.6 cos inverse, that is giving me 53 degree, 53.13 degree. Okay. Now if you put n equals to 2, then nothing will be satisfied. You can try putting n equals to 2. What you are getting? Plus minus 1 plus minus 3.2. Then you take, first you take plus sign, then you take minus sign. That you first take plus here, then another plus here. Then you first take plus here, then minus here. Then you take minus here, plus here, minus minus you take. No value will be satisfied. So only till this point we need to solve. So what is our answer? Our answers are, our final answer are, theta should be equal, theta can be 0, pi, or let's start again by the degree. That theta could be 0 degree, it could be 53.13 degree, it could be 126.86 degree, and it could be 180 degree. So these two functions will be equal at theta equals to this. Okay, are you getting this point? Well and good. So these calculation will be used in our analysis. That's why I did this. Now we will study about radiation pattern. So I will take a pause. You can also take a pause because it's been a very long time. Then we will start studying about radiation pattern. Or shall we do it in next lecture? No, it will take another 1 hour, I guess. So you can study it tomorrow, but I will deal this particular concept in this video only. So this is the next concept about radiation patterns. Okay, yeah. Yeah, so let's start the third half of this video. So in the previous half, what did we saw? In the end, we saw a mathematical calculation that if some function cos A equals to cos B is given, then what is the relation between A and B? And before that, we studied about our linear dipole antenna, and we studied for length greater than lambda by 10. Now we need to see the radiation pattern. So in radiation pattern, what do? we first calculate the normalized value of electric field. Then we plot it with respect to theta and with respect to phi. When we plot it with respect to theta, at that time we take phi equals to 90 degree, and when we plot it with respect to phi, at that time we take theta equals to 90 degree. We call this as E plane and this as H plane. Now why do we call it E plane, why do we call it H plane, why do we take theta equals to 90 degree, why do we take phi equals to 90 degree? All these things have been explained in the previous video, right? During the Hertzian dipole, I have already explained the basics of radiation pattern. So I'm not gonna spend that time on basics of radiation pattern. I'm gonna spend time on telling you how to draw the radiation pattern for these linear dipole antenna, and the length we will be taking, that would be greater than lambda by 10. That means we will be taking half wave, full wave, quarter wave, monopole, dipole, 3 lambda by 2 length, 1.25 lambda length, all these kind of lengths we are going to take. Is that clear to you? So what is our first task? We need to write down the normalized value of E field. So for Hertzian dipole, what was our normalized value of E field? Sin theta, right? This was for Hertzian dipole. And what was the expression of E field for Hertzian dipole? That was ideal sin theta upon 4 pi r, j beta was also there, e to the power minus j beta r, a theta gap. This was the expression. So here there was only one term. This sin theta term was the function of theta or phi. This was the function of theta or phi. Although it is not a function of phi, but certainly it was a function of theta. So that was our normalized impedance value. Now in this case, for linear dipole antenna, what is your expression of E? J I naught upon 2 pi r, f theta, e to the power minus j beta r, a theta gap. So here what is the function of theta? Which term is the function of theta? Theta or phi? You just need to see the term which is a function of theta or phi in your electric field expression. So which term is the function of theta or phi? This, f theta. So what is your normalized value of E? F theta. For any linear dipole antenna having length greater than lambda by 10, this is your normalized value of E, that is f theta. And what is f theta? That you would already be knowing, that is cos beta L by 2 cos theta. So here I am taking a random length. After that I will take special cases like lambda by 2, lambda, 3 lambda by 2. These special cases I am going to take. But as of now I am writing it down for a particular length. So that will be the expression. There you go, right? Very easy. So normalized value of E field is given. So now for particular cases we are going to find out the normalized value of E field, then we will find out the position of nulls, and then we will draw our radiation pattern, right? You know how to find the value of nulls, how to find the position of nulls. What do? You keep it equals to 0. If you keep it equals to 0, then you can find your value of nulls as well, or your position of nulls as well. So let's start with the first one. We are taking the length to be half wave dipole antenna we are going to see. That means my length is lambda by 2. So what will be my normalized value of E? So I hope you already remember it, or you can calculate it as well. It will be cos pi by 2 cos theta divided by sin theta, right? This is your normalized value of E. Now if you need to find the location of nulls, what you need to do? You need to keep it as equals to 0. So from there what you are getting? Cos pi by 2 cos theta is equals to 0. So when cos is 0, so always when there is a question based on trigonometry, so whenever there is a question based on trigonometry, I always prefer making a graph. So first I will make a graph of cos. So at that side as well I can make the graph of cos. So I know that first time it will be becoming 0 at pi by 2. So my pi by 2 cos theta, first time it is becoming 0 at pi by 2, then it will become 0 at 3 pi by 2. So I always will make a graph whenever I am solving a problem on trigonometry from any subject. So in the examination, if I need to solve these kind of things, I always prefer making a graph. This is something that I do. So I will make a graph. Okay, so you can also proceed in the same manner. So roughly you can make a graph, and after that you can see what is the next time it is becoming 0. So in that manner you can write down. Now next time would be 5 pi by 2. Certainly it will not be only positive, it can be negative as well. So positive, negative, positive, negative, positive, negative, right? So now from here what you can see is that your cos theta is getting out to be plus minus 1. Cos theta could be plus minus 1. If you take pi by 2 in action, so what will happen? Pi by 2 and pi by 2 will get cancelled. Cos theta is plus minus 1. If you take 3 pi by 2 in action, so what will happen? Pi by 2 and pi by 2 is getting cancelled. Cos theta is becoming plus minus 3. After that it will become plus minus 5. But this is not possible, no? Plus minus 3 is not possible because the value of cos theta can be from minus 1 to 1 only. Range of cos theta is from minus 1 to 1. This value is plus 1, this value is minus 1. So it can never be plus minus 3, it can never be plus minus 5. So those values are gone. Only possible thing is cos theta could be plus 1 or minus 1. So when cos theta is 1, at that time what is the value? When cos theta is 1 at 0 degree. And when cos theta is minus 1 at 180 degree. Now you will say that sir, cos theta is 1 at this angle as well, which is your 360 degree. So will I take 360 degree in action? Like it could be 360 degree, it could be 720 degree as well. But I will not take these things in action because I know that my range of theta is from 0 to pi only. I always know that my range of theta is from 0 to pi. This I told you like 100 times. My range of theta in spherical coordinate system will be from 0 to pi only. So I will only take till pi. That's it. So what are the two answers that I am going to take? That is 0 degree and 180 degree. So my position of nulls are 0 degree and 180 degree. Position of nulls. Now I will tell you a line that you will always remember. What is that line? That between two nulls there will be a maxima. What I am saying? Between two nulls there will be a maxima. Let's just say at theta equals to theta 1 you are getting a null. This theta 1, it could be anything. Let's just say it is 30 degree. And at theta equals to theta 2 you are getting another null. It could be anything. At theta equals to theta 2 you are getting another null. It could be anything. Let's just say it is 150 degree. So in between them there will be a maxima. At null what will be the value? 0. At this null value will be 0. So this kind of lobe you can get. So in between there will be a maxima. Are you getting this point? Between two nulls there will be a maxima. Because using this expression it will be very tough to find the maxima. Why is that so? Because what you need to do, if you need to find the maxima of this value, what you need to do, first you need to differentiate with respect to theta. Then from here you will get a value of theta, and that theta value you will put here, and that will give you the maximum value, and also you will find the value of theta where it is maximum. So this expression is, it is a bit easier, but what if this guy also comes in action? Then the expression will become difficult, then this differentiation and all these things you cannot do. So always you remember one thing, between two nulls there will be a maxima. And if you actually need to find the value, then you need to differentiate it and then put it equals to 0, and from there you get the value of theta, and that will be the location of maxima. This thing we do in mathematics. Whenever we need to find maxima, what do? We differentiate and then put that equals to 0. From there we can find the value of x. In this case it would be theta. So that differentiation we are not going to do. We just know one thing, that between two nulls there will be a maxima. So always you need to keep this thing in mind. So here what is the location of our nulls? 0 degree and 180 degree. So now what is this? Theta equals to 0 degree. What is this? Theta equals to 90 degree. What is this? Theta equals to 180 degree. And what about this? This is also theta equals to 90 degree. Right? So at 0 degree you are having 0 value. At 0 degree, at theta equals to 0 degree you are having 0 value. At 90 degree what value you are having? You don't need to find it out that at 90 degree I am having what value. I just know that this is my, what I know, that sir, this is my minima, or you can say this is my null and this is my another null. So between two nulls I will be getting a maxima. So this kind of pattern I will be getting. Say yes or no. Between two nulls I will be getting a maxima. So this kind of pattern I will be getting. Or you can check as well at theta equals to 90 degree. If you put theta equals to 90 degree, what you are getting? Cos 90. What is the value of cos 90? 0. Sin 90 is 1. So cos 0 is 1. So at 90 degree you are getting it to be 1. So this is the maximum value you are getting at 90 degree. And similar thing will happen this side as well, because this is symmetric. This you are going from 0 to 180. Same thing you are going from here to here as well, 0 to 180. So again it will be symmetric. So what kind of pattern we have made here? E-plane pattern. Is it the same as that we got in Hertzian dipole? In Hertzian dipole as well we are getting the same expression, right? Hertzian dipole as well we were getting the same kind of radiation pattern, but there is a difference that I will tell you. But first let's this we have made E-plane. Now we are going to make H-plane as well. So E-plane we have made. Now let's make H-plane. So what do you think? Try making H-plane on your own. What do you think? What will happen in H-plane? What do we do? What is your f theta? At theta equals to 90 degree, at theta equals to 90 degree, f theta is 1 only. At theta equals to 90 degree, f theta is 1. And that you need to plot versus phi. and phi value will start here. Phi value is 0 degree, here phi value is 90 degree, in between it will be 45. Here this phi value is, this is 90, this is 270, and somewhere here phi value will be, if you talk about this point, this will be phi equals to 180 degree, and then again it will be 360 degree. So no matter whatever the value of phi you take, no matter whatever the value of phi you take, it will always give you a circle only. Sorry, not circle, it will always give you a value of 1. Whatever the value of phi you take, even if you take phi equals to 0 degree, the magnitude is 1. If you take phi equals to 90 degree, the magnitude is 1. If you take phi equals to 180 degree, magnitude is 1. If you take phi equals to 60 degree, magnitude is 1. That means you rotate around phi, magnitude is always 1. What does that mean? You will get a circle. The same kind of thing we have seen in our Hertzian dipole as well. There also we were getting the same circle. Say yes or no. Do you agree to my point? Certainly you agree to my point. So there will be a circle. So from now onwards we are never going to make H plane. Why is that so? Why do you think we are never going to make H plane? Because what will happen? What is our f theta? That is cos, for a random length I am saying, cos beta l by 2 cos theta minus cos beta l by 2 divided by sin theta, right? Now let's just say I put for making H plane pattern, what I need to put? Theta equals to 90 degree. So sin 90 will be 1. This will be 1. This will also be 1. So what will be the H plane pattern? 1 minus cos beta l by 2 divided by 1. This is your f theta for H plane. For H plane, what this is? This is your H plane. So for H plane, this will be your f theta expression. That means this will be your normalized value of E. Now this normalized value of E will be a fixed quantity, you know, because 1 is fixed, this is also fixed, and this will also be fixed. So it is a fixed quantity. Now if you vary the value of phi, this is not a function of phi. If you put phi equals to 0 degree, or if you put phi equals to 90 degree, if you put phi equals to 60 degree, if you put phi equals to 180 degree, if you put phi equals to 270 degree, if you put phi equals to 240 degree, always it will give you a fixed value. That means it will always be a circle. So in H plane, you will always get a circle only. Are you getting this point? So that's why we are never interested in making H plane pattern. I have made H plane pattern for Hertzian dipole. I have made H plane pattern for lambda by 2 or half wave dipole as well. But from now onwards, I am never going to make H plane pattern, because you already know that it will be a circle only. Because your normalized value of E is not even a function of phi. If it is a function of phi, then it will vary with respect to phi. But here it will not vary, right? Now after that, what happens is that we tell what we do. We say that this we have made for, this pattern we have made for theta equals to, sorry, not phi, theta equals to 90 degree. This pattern has been made for theta equals to 90 degree. And what about this pattern? This pattern has been made for phi equals to 90 degree. But it is not necessary that phi will be 90 degree only. Phi can take any value from 0 to 360 degree, and theta can take any value from 0 to 180 degree. So if you take different values, then what do you get? In a conic way, in a conic section, we are going to get circles. So this is how we get circles if we take the other values of theta. So this we have made for theta equals to 90 degree. But what if I take theta equals to 45 degree? Then this kind of circle I will get. Then this kind of circle I will get. This kind of circle I can get. Similarly, downward as well, I can get these kind of circles. And what about these things? So these are two circle kind of structure. These are not perfect circle, but these are some kind of circle kind of structure. When I vary the value of phi, then these circles will rotate. So from here to here, in this manner, these circles will rotate. So basically, these circuit will rotate like this. From here, in this manner, it will rotate. And complete animation, not animation, complete 3D structure I have given you in the last lecture. This is exactly ditto same as Hertzian dipole. We are just repeating it. In Hertzian dipole, whatever the concept that I taught, I spent a lot of time. So you can go and check out the radiation pattern of Hertzian dipole. So there I have taught the same thing, and the same kind of pattern you are getting there. Ditto same kind of pattern. I showed it in 3D view as well, that how this pattern is looking like. Do you agree to my point? Say yes or no. So there will be circle, circle, circle like this, and it will be moving completely. So this kind of radiation pattern will be shown in 3D. This diagram and this diagram we have made in 2D only. But when we show it in 3D, circles, there will be a lot of circles going upward, and those two circles will be moving around. So this is how it will be looking in 3D. And you can see that where is your antenna. In this diagram, I did not show the antenna. Where will my antenna in this diagram? In this particular diagram, my antenna will be here. along z axis. This is my antenna. Yeah, so this is my antenna. This is my antenna. In this diagram, this is my antenna. So around the antenna, you are getting the radiation pattern, but you can see that along the axis of antenna, here also you can see that there is a kind of hole. So along the axis of antenna, there is no radiation, but around the, like this is my, let's just say this is my antenna. So along the axis of antenna, like from here to here, there will be no radiation. From downward as well, there is no radiation, but around it there is complete radiation. You can see those circles will be around this antenna. Around this antenna, there will be circles. And here also you can see that around this antenna there will be these two kind of structure that will be moving around. Are you getting this point? So these two kind of circle will be moving around, and that will be moving around in a circle in that manner. So this kind of 3D structure you are getting. Although it is not useful for your examination, but at least it should be clear that how does the radiation pattern looks like, because in the examination statements can come that in a Hertzian dipole antenna or in half wave dipole antenna, you get the maximum radiation at theta equals to 90 degree, or they can write down you get maximum radiation in the perpendicular direction to your antenna, in the perpendicular direction to what your antenna is placed. So if my antenna is placed like this, then maximum radiation is there in this direction, right? If my antenna is placed like this, then maximum radiation is here, right? Same goes for Hertzian dipole as well. Or what they can say, that along the direction of your antenna, along the arms of your antenna, the radiation is 0. This statement is also true. So these kind of statement wise question can come. In H plane, you are always getting a circle. Yes, because my normalized value of electric field is not even a function of phi. So no matter how phi changes, I will always get a constant value. So those will be always a circle. So these kind of circles I will be getting, and this kind of final pattern I will be getting. So this thing till this point we have only repeated what we have studied in our Hertzian dipole, right? So this is same as radiation pattern of Hertzian dipole antenna. But tell me one thing now, what is the difference? Because normalized value of E field was different, no? Normalized value of E field for Hertzian dipole was sin theta, and for this it is this value, not this value, sorry, this value. So normalized value of E field is different. So this structure cannot be same. Are you getting this point? There is a difference in the structure because normalized value of E field is different, no? So now I will show you the difference. What is the difference? So this was our normalized value of E field. This was our normalized value of E field for Hertzian dipole, and this is our normalized value of E field for half wave dipole. So if you superimpose both of the structure, then this is how it looks like. That this is for your half wave dipole and this is for your Hertzian dipole. Somewhere I have seen that some people say that, sir, this would be for half wave dipole and this would be for Hertzian dipole. That doesn't make any sense. Like what I have seen is that, sir, this is your antenna, and for for half wave dipole the radiation will be far away, but for your Hertzian dipole it will be lesser. Do you really think it is true? No, it is not true. Why is that so? Why is that so? Because what is this? This is your z axis. What is the value here? Theta equals to 0 degree. And what is the value here? Theta equals to 90 degree. If you put theta equals to 90 degree in this expression, at theta equals to 90 degree, what you are getting? F theta equals to 1 only. And at theta equals to 90 degree, or F theta, or you can say normalized value of E field. Normalized value of E field. What you are getting? 1 only. And here also what you are getting? 1 only. So here you are getting the same. That means if this is my Hertzian dipole and this is my half wave dipole, so radiation distance is same. Like at this point only you are getting maximum radiation in both of the cases. So like some people say that this will radiate to far distance, lambda by 2 will radiate to far distance, and Hertzian will radiate to lesser distance. This does not make any sense. So this is not true. If you have studied this somewhere, then you can modify your notes. Both will be superimposed. Just the difference is this lobe width, this lobe width is come. What I am saying, it is less. I said come. So this lobe width is less for half wave dipole, but it is more for Hertzian dipole. This lobe width. What is this? This is your lobe width. So this lobe width is lesser for half wave dipole and it is more for Hertzian dipole. This is the difference. And lesser the lobe width, more the directivity. Lesser the lobe width, more the directivity. Now what is this directivity? That we will study in the next lecture. So as of now, you don't need to worry about directivity. So there I will tell you what is the actual meaning of directivity. What people think is that directivity means how far someone is radiating. No, this is not the meaning of directivity. Directivity has different meaning. It shows how concentrated your radiation is. What does directivity show? That in a particular direction, how concentrated your radiation is. So here the lobe width is smaller, that means it is more concentrated. And if lobe width is larger, that means it is lesser concentrated. That means let's just say if this is having 50 watt power and your Hertzian dipole is also having 50 watt power, and in this particular direction, who is radiating more power? Because it is more concentrated, that means it is radiating more power. This is your lobe of a antenna, right? So this lobe contains 50 watt power. Now the smaller the width, that means it is more concentrated. And if width is larger, let's just say if width was something like this much was the width, then at theta equals to 90 degree, the radiation will be lesser. That means you will be getting lesser power. If you are standing here, then both are radiating 50 watt power only. But here if you are standing, then you will get more power from half wave dipole than the Hertzian dipole. And what is the reason behind that? Because lobe width is smaller. If lobe width is smaller, that means it is concentrated more towards 90 degree. So lesser the lobe width, more will be the directivity. So directivity of your half wave dipole antenna is more than the Hertzian dipole antenna. Directivity has nothing to do with this thing. No, absolutely wrong. Both will be ending at a certain point only. But still the directivity of half wave dipole is more. The reason is it is more concentrated. It doesn't mean that it will be radiating far away. No. So again I will repeat all these things. Same thing I am going to repeat. I have told the complete concept. I have also told you what is the meaning of directivity, right? I hope you must have understood the meaning of directivity. Directivity shows how concentrated your radiation is in a particular direction, right? Or in the better definition would be how concentrated your radiation is, not in a particular direction, in the direction of maximum radiation. That is your directivity. And what did I say? That how concentrated your radiation is in a particular direction, that is known as directive gain. And what is directivity? That how concentrated your radiation is in the direction of maximum radiation. So don't get confused as of now. Again, all these things will be repeated with certain formula with the actual meaning. I will teach you the antenna parameters in the next lecture. So those antenna parameters are usually taught with respect to definitions. Like people mug up the formula that antenna radiation, this formula is there, this question is there, and this is how you need to solve the problem. But if you don't know the meaning of all these parameters, then you might mess up in the examination. So we will see the meaning of all these things: directivity, directive gain, radiation intensity. We will see the actual meaning, and certainly we will solve a number of problems as well. But understanding the meaning is also important. Yeah. So here I told you the difference between both of the antennas. Like, right? This is your half wave dipole, this is your Hertzian dipole. So here the lobe width is lesser. So this I can write down: lobe width, or directly I am writing directivity of lambda by 2 is more than Hertzian. Okay, you will be able to understand what is directivity. So when you revise, you would know what is the meaning of directivity, how concentrated is your radiation in the direction of maximum radiation. Okay, so that is your directivity. Is that clear to you? So let's go to the other full wave dipole antenna. That means now the length is equals to lambda. So can you find out the value of f theta? Certainly you can find it out. What you need to do? 2 pi by lambda, 2 lambda into lambda cos theta minus cos, what we are getting here, cos pi. Cos pi is minus 1 only, divided by sin theta. So f theta is cos pi cos theta plus 1 divided by sin theta. Well and good. Now what I need to find? I need to find the position of nulls. This is your normalized value of E field as well. So if I need to find the position of nulls, what I need to do? I need to put that equals to 0. So in the examination, mostly from radiation pattern, what questions can be asked? Position of nulls. That is very important. Or directly they can ask you to make the E-plane pattern. They can ask you to draw the E-plane pattern, or they can ask you the position of nulls. Okay. So these two things, I guess, that can be asked in your examination. I don't think they will ask you the normalized value of E field. They will directly ask you the position of nulls, and for that you need to find the normalized value of E field, right? So cos pi cos theta would be equals to what? -1. If I put that equals to 0, then sin theta will be gone. Then cos pi cos theta would be equals to -1. So from here, what you are getting? So when it is -1, pi cos theta could be equals to, you can make the graph always like this. So what is this value? Pi. What is this value? 3 pi. So it could be -1 at pi, 3 pi, 5 pi in this manner, but not only plus minus sign will also be there, right? Not only positive value, plus minus sign will also be there. So you can always make a graph. When we make a graph, it becomes more clear to us. So again, what you can see, cos theta can be equals to plus minus 1. Why is that so? Because it cannot be plus minus 3. It cannot be plus minus 5. Well and good, right? So again, the position of nulls are getting 0 degree and 180 degree. So position of nulls is same for Hertzian dipole, for half wave dipole, and for full wave dipole. Say yes or no. Position of nulls are same for Hertzian dipole, half wave dipole, and full wave dipole. All the position of nulls are same. Do you agree to this point? Certainly you agree to this point, right? So 0 degree and 180 degree, ditto same graph you will be getting. Same graph. Like if you put 90 degree, if you put cos 90, if you put 90 here, so what it will become? Cos 0. Cos 0 is 1, 1 plus 1 is 2. Here if you put cos 90, what that would be? Sorry, if you put 90, what I am finding is that I am finding normalized value of E at theta equals to 90 degree. So what that would be? At theta equals to 90 degree. What that value would be? If you put cos 90 here, cos 90 is 0. Cos 0 is 1. 1 plus 1 is 2. 2 divided by sin 90. Sin 90 is 1. So what is that value? 2. So this value is 2. In the previous case, what was this value? This value was 1. This was theta equals to 0. This was theta equals to 90 degree. So here what value we were getting? 1. Now here what we are getting? 2. So now if I make my radiation pattern for full wave dipole, so that will go something like this. That can be ahead because the value is 2, no? Although if this much length is 1, that means this much length cannot be 2. It will be more, it will be like roughly around doubled. What I mean to say is that the radiation pattern will go something like this, something like this. So now it is fine. Now you can say that radiation pattern will be covering more distance now. So that is fine now. But for half wave dipole and for Hertzian, both will be covering the same distance. Here what is the maximum value? At 90 degree maximum value is 2. Here also you are getting the value of 2 only. So now this is covering more distance. That means this will be more, like it will be more concentrated, no? Like previously this much was the width, then this width became, now this width has become. For Hertzian dipole this was the width, then this, now this is the width. So they are more concentrated towards a particular direction, or you can say towards the direction of maximum radiation, because this is the direction of maximum radiation. At theta equals to 90 degree you are getting the maximum radiation. Now someone will be having the doubt that sir, why we are not calculating half power beam width? Why we did not calculate half power beam width in this case? Try calculating it, it will be very tough. What I will do for calculating half power beam width? I will put this equals to, this equals to 1 by under root 2 and divided by sin theta is also there. How can you get the value of theta from here now? Can you solve this mathematical equation? For calculating half power beam width, what you need to do, you need to put E of n, normalized value of n equals to 1 by root 2. Not practically, mathematically can you get this answer? It is very tough. If I tell you that at theta equals to this much angle, you are getting your half power, then you will say that sir, okay, I can put that theta value here and then I will be satisfied with that. But can you do the mathematical calculation like this? If there are 4 options, then you can match. But if I ask you directly that calculate the value of theta, I give you this equation and I ask you to calculate the value of theta. Is that possible for you? No. So half power beam width will never be asked in such cases. If half power beamwidth is asked, that means the normalized value of E field will be very easy, like it could be sin theta. So in Hertzian dipole case, they can ask you the half power beamwidth. Why is that so? Because this is sin theta and you can put it equals to 1 by under root 2. That means theta is equals to 45 degree. So at theta equals to 45 degree and at the other angle as well, you will get your half power. So half power beamwidth is 90 degree there. So that is very easy, that is very straightforward. But here if you put equals to 1 by root 2 or minus 1 by root 2, then it is not that easy to solve. Here 1 by root 2 is very easy to solve. Because sin theta equals to 1 by root 2, where do you get? At 45 degree you get, and next you will be getting at 135 degree, right? So yeah, 135 minus 45, that will be 90 degree. That is very easy to get the answer. Are you getting this point? But here it is not that easy. So that's why in such kind of cases, you will never find that they will ask you the half hour beamwidth. In some test series, I have seen some questions that what is the half hour beamwidth for half wave dipole antenna? But GATE examination will never ask it. Why do they ask? Because it is mentioned in the textbook. When you open the Balanis book, when you open the book of Balanis is a very good book for antenna theory. So there those values are mentioned, but you are not supposed to remember the values. Whatever that you are supposed to know, that I will tell you. You are supposed to know the relation between the half hour beamwidth of half wave dipole or full wave dipole or 3 lambda by 2 dipole, relation between the directivity of these kind of antenna. So that relation you are supposed to know. You are not supposed to know the exact value. So that's why we are not calculating the exact value of half hour beamwidth. Now if I ask you this question, that who is having more half power beamwidth, half wave dipole antenna or Hertzian dipole antenna? What you will say? Which antenna is having more half power beamwidth, half wave dipole antenna or Hertzian dipole antenna? What will be your answer? What will be your answer? The answer will be Hertzian dipole antenna. Why is that so? Why is that so? Because here half power will be somewhere here and here half power will be somewhere here. So this width will be smaller, no? Like for Hertzian dipole, this is the width. For half wave dipole, this is the width. So smaller the width, smaller the lobe width, smaller the lobe width, smaller the half power beam width. If lobe width is small, that means half power beam width will also be small. Are you getting this point? So who will have more half power beam width? Hertzian dipole will have more half power beam width, right? So what do you think? What will be the relation between directivity and half power beam width? So the relation between directivity and half power beam width will be inversely proportional. So all these kind of things again we are going to see in the next lecture. But here I am building a base that how these kind of things are coming. Everything is coming from radiation pattern. So that's why time should be spent on this particular topic. That what is the actual meaning of radiation pattern and why do we focus on E plane only? Why we don't focus on H plane? Because they are not the function of phi. So are you getting the point here? Right? If you know how to make the radiation pattern, then mostly questions you will be able to answer. Well and good. Okay then. This is the lobe width, theta equals to 90 degree. Everything we have studied. Okay, fine. Yeah. So yeah, this E plane pattern we have made. E plane pattern we have made. E plane pattern we have made for length equals to lambda. Now the next would be 3 lambda by 2. So do it on your own. Next length is 3 lambda by 2. So find the position of nulls, draw the pattern, try doing it on your own. Certainly I will also tell how it will be made. But try doing it on your own once. Okay. So let's start. I hope you must have done it. So what I need to find? F theta I need to find. This you must have found out. If you are not able to find out F theta, then it is very tough now. If you are not able to find F theta, then I don't think you should be continuing this lecture. Okay, really sorry to say that, but till now you should be comfortable with this, right? So what that would be? 2 pi by lambda into 3 lambda by 4. So what this would be? 3 pi by 2, cos 3 pi by 2. So it would be cos 3 pi by 2. Cos 3 pi by 2 cos theta minus cos 3 pi by 2 divided by sin theta. What is the value of cos 3 pi by 2? You can always make a graph. This is pi by 2, this is 3 pi by 2. Pi by 2 plus pi, that is 3 pi by 2, 0. So this can be always ignored. 2 pi by lambda into 3 lambda by 4. Yeah, 3 pi by 2 only. Not having confidence on my calculation. Yeah, okay. So position of nulls, let's find out the position of nulls. Okay. Okay, then for position of nulls, what I need to do? E of n should be equals to 0. That means cos 3 pi by 2 cos theta should be put equals to 0. So from here what I am getting? 3 pi by 2 cos theta. This could be equals to what? 0. When do you get 0? Pi by 2, 3 pi by 2 in that manner. So pi by 2, 3 pi by 2, 5 pi by 2. In that manner we need to keep on going. 7 pi by 2. But certainly don't forget the plus minus sign. Well and good, because same graph will be in the negative as well, right? Okay, then now what they are asking? They will ask the value of cos theta. So from here, what do you think? What will be the value of cos theta? So if I see the first one, so pi by 2 to pi by 2 is getting cancelled. So cos theta could be equals to plus minus 1 by 3. Say yes or no? And from here, cos theta could be equals to plus minus 1. From here, cos theta would be equals to plus minus 5 by 3, which is not acceptable. So this is not acceptable. So only these two values I need to put. These two values I need to take. Cos theta equals to plus minus 5 by 3. Sorry, cos theta equals to plus minus 1 by 3 and cos theta equals to plus minus 1. So cos theta is equals to 1 by 3. Cos theta equals to minus 1 by 3. Cos theta equals to 1 and cos theta equals to minus 1. And making sure that your theta is from 0 to 180 degree. So what you are getting? Position of nulls. Cos theta is 1 by 3. So cos inverse 1 by 3. You need to use calculator. $70.52. $70.52 degree. Reciprocal plus minus cos inverse. For this it is 109. For this value, what is the value of theta you are getting? 109.47 degree. What about this one? Cos theta is equals to 1. When do you get it? Cos theta equals to 1. So that you get at 0 degree, and minus 1 you get at 180 degree. So these are your position of nulls. These are your position of nulls. So if I make the coordinate, theta equals to 90 degree means zx plane, zy plane, sorry, zx. I am not writing x. I hope I am not writing x. Arey yaar, again and again I am writing x here. Here I wrote y. Sorry, wait a second. Phi equals to 90 degree. This would be y, no? Really sorry. Here I did a blunder. This would be y, right? This would be y. This would be y. This would be x. Okay, this is x, y, z only. Okay, this 3D we are making x, y plane. This is fine. This would also be y. Okay, z, y plane, right? Phi equals to 90 degree. What is that plane? Phi equals to 90 degree. Z, y plane only, no? That was my error. Phi equals to 0 is x, z plane. Phi equals to 90 is y, z plane. This we have already seen in the previous lecture. That was the error. So yeah, this will be your y, z. This is your theta equals to 0 degree. This is theta equals to 90 degree. And this is theta equals to 180 degree. So what all are the position of nulls? So one null is at 0 degree. Another one at 180 degree. Now there are another null 72.50. So roughly around this one 72.50, right? Then 109.47, roughly around like this 109.47. So this is your theta equals to 70.52 degree, and this is your theta equals to 109.47 degree. What do you think? How many lobes will come? How many lobes will come? What did I tell you? Between two nulls, there will be one maxima. So at 0 degree you are having null, again you are having null. that means between two nulls there will be one maxima. Between two nulls there is one maxima. Same goes here, between two nulls there will be one maxima. And between two nulls there will be one maxima. Same thing will be repeated here as well, no? Like here as well the same thing will be there, because this is theta 90, 180, this is your also your 90 and 180. Now I know you are having some doubt. What is that doubt? That sir, how did you get to know that sir this width will be smaller and this width will be larger? How did you get to know this thing? That sir, why did you take this as larger one and this as the smaller one? Because I am saying that this is covering more distance, this is covering less distance. So how will you get to know this thing? You need to put the value. In this expression, put theta equals to 90 degree. What is your En? This is your En, no? This is your normalized value of E field. Normalized value of E field is cos 3 pi by 2 cos theta. Cos 3 pi by 2 cos theta divided by sin theta. Okay. So if I put theta equals to 90 degree, if I put theta equals to 90 degree, what I will get? Sin 90 is 1, cos 90 is 0. So what value I am getting? 1. So this value is 1. Now at this value, I am not sure what is this value. I am not sure about this angle. But at this value, I was getting more value. At this, let's just say this angle is somewhat around. I am not sure what is that value. I am taking any random value. Let's just say this is 35 degree. At 35 degree, you are getting more value of normalized value of En. If you put cos 35 here, let's try getting out. Here, what did you get? 1. Let's try taking theta equals to 35 degree. What I am taking? Theta equals to 35 degree. This is what I am taking. So 35 cos 35 into 3 pi by 2 into 3 divided by 2 into pi, and then take cos of that. This is in radian, take cos of that, divided by sin 35. Sin 35, right? Sin 35. Yeah, you are getting 1.31. At 35 degree, you are getting 1.31. This is what you are getting. Normalized value of E field. So certainly you get to know that at 90 degree, you are getting lesser value. That means maximum radiation is in this direction. Are you getting this point? Maximum radiation is in this direction. Like whatever that is happening here, same thing will be happening here as well. No? Basically, radiation pattern will be what if you make the radiation pattern in this half. If you can make the radiation pattern in first quadrant, then you would know that same will be copied in the second quadrant. Sorry, same will be copied in the fourth quadrant, and one first quadrant and fourth quadrant, that will be copied same in second and third quadrant. So same thing will be happening downward as well. So how did you get to know that sir this lobe will be lesser? So for that you need to put random values, and certainly this will not be asked in the examination. Are you getting this point? Are you understanding this point? Here there are 3 lobes. Now I told you a practical method that how to find that this is having more value and this is having lesser value. That put the value theta equals to 90 degree, theta equals to 35. I took a very random value. In between 0 to 70.52, I took a very random value, that is 35 degree. And then I put the value there, I go to know that I am getting more magnitude. That means it is radiating more in the 35 degree direction than 90 degree direction. So if I am having a 3 lambda by 2 length antenna, then where will I put my receiving antenna? Will I put it at theta equals to 90 degree? No, I will put that at theta equals to 35 degree, because I need maximum radiation. So for me, the matter of interest will be this lobe, not this lobe. Why is that so? Because this is giving me the maximum radiation. That's why this is my matter of interest now, or this is my matter of interest. I can put my antenna either here or here. Which antenna I am talking about? I am talking about my receiving antenna. Are you getting this point? So randomly I put the value. So these kind of things will not be asked in the examination. Are you getting this point? If they ask, then they will tell that in the direction of theta equals to 35 degree, you are getting the maximum radiation. This is again a very random value. I just wanted to check if I am getting more radiation or not. So somewhere in between I took it, and then I got to know that I am getting more radiation at theta equals to 35 degree than at theta equals to 90 degree. So this is your maximum radiation. Now what is first null beam width? First null beam width. You can make the same pattern at this side as well. I am not making it because this will be symmetric only. Now let's go here. if I ask you what is the first null beam width there, first null beam width, you will say that, sir, at 0 degree there was null, at 180 degree there was null, 180 degree. In this case as well, what you will say, what is first null beam width? That is also 180 degree, because sir, at 0 degree there was a null, at 180 degree there is a null. So first null beam width is 180 degree. But if I ask you the same question for this case, then this can be your first null beam width, this can also be your first null beam width, and this can also be your first null beam width. Like there are three contenders. If you need to find the beam width between the nulls, what I am saying, if you need to find the beam width between the nulls, then theta degree and 72.50, what could be the answer? 70.52 degree. The difference between these two nulls, then difference between these two nulls, then difference between these two nulls. So here also you will get 70.52 degree only. Here also you will get 70.52 degree only. Here what you will get? 72.52, 109.47 minus 72.52. 109.47 minus 70.52. So you are getting 38.95. So this is your 38.95, this is 70.52, and this is also 70.52. What do you think? What will be my answer? There are three lobes. In the previous cases, there were only one lobes. Here there were only one lobes, and I don't need to care about when I used to calculate first null beam width, because this minus this, that is my answer. Now in this case, what will be the answer? So I am always concentrated towards the maximum radiation. Where is my maximum radiation? Here is my maximum radiation. Here is my maximum radiation. So I will calculate the first null beam width with respect to the maximum radiation. And where is my maximum radiation? Here. Here. So what will be my first null beam width? That will be 70.52 degree. I will not take this in action, because this width you are getting with respect to the minimum radiation, but you are always concentrated about maximum radiation. Let's just say I was getting so many lobes. Here we were getting 3 lobes. Previously we were getting only 1 lobe, but it may happen that you are getting so many lobes, like this, like this, like this, like this. There are so many lobes. So what you will see, in these lobes where you are having the maximum radiation, here you are having the maximum radiation. So this is your one null, this is your another null. So this width will be your first null beam width. So that's why the name is first null beam width. The beam width between first nulls. And what do you mean by first nulls? The nulls with respect to the maximum radiation. Those are your first nulls. Are you getting this point? All these are very, very conceptual things. In antenna we find tough because we don't understand these things, and we directly jump onto antenna array. So all these things I will be relating with respect to antenna array as well. Okay, so this is very, very important. And with respect to these things only, antenna parameters are defined. Directivity and radiation pattern. Radiation pattern we are already studying. Radiation intensity, all these are defined with respect to radiation pattern only. Are you understanding this point? So if they ask me what is my first null beam width for this particular question, then answer would be 70.52 degree. Now again in the examination, let's make it more clear first. Again in the examination, you would be knowing this thing, that this is my f theta. You can do this calculation, you can do this calculation as well, and then you can make the pattern as well. But in the examination, again you would not be knowing that which lobe will be having the maximum radiation. What I am saying is that in the examination, again you wouldn't be knowing that which lobe will be having maximum radiation. You will get to know that there will be 3 lobes. You will get to know that there are 4 nulls. But what if some student make the radiation pattern like this, that here lesser radiation and here maximum radiation? What if someone makes like this? Because he don't know what values he is getting. So mostly like 99% chances are there that they will mention that in this direction you are having maximum radiation. They will mention it. Or even if they don't mention, then you need to put random values. That one random value I will put between these 2 nulls, that means theta equals to 90 degree, and one random value I will put between these 2 nulls, that is theta equals to 35 degree. Then I will get to know that I am having more radiation in theta equals to 35 degree. That means this will be my major lobe and this will be my minor lobe. They are known as major lobe, minor lobe. Okay. So that value, either it will be mentioned in the examination or I can put from my side as well. Are you getting this point? Okay. So this could be your major lobe. This is your major lobe and this is your minor lobe. But mostly what I feel is that till now they did not ask any question from first null beam width, but whenever they ask, and if there are more than 1 lobe, here there are 3 lobes, here there were only 1 lobe. If there is more than 1 lobe, then what I feel is that they will mention where is the maximum radiation, and even if they don't mention, then you will put a random value of theta and you will get to know that where is the maximum radiation. Are you getting this point? And with respect to the maximum radiation only, you will define your all the values. You will define your first null beam width. Even half power beam width is also defined with respect to the maximum radiation only. What I am saying, half power beam width is also defined with respect to the maximum radiation. That means for half power beam width, you will calculate this much width. Half power means this is the maximum value. This is the maximum value. What will be 1 by root 2 of this maximum value? What will be 1 by root 2 of this maximum value? So you will find out this width. This width will be your half power beam width. So half power beam width, directivity or first null beam width, all the antenna parameters are defined with respect to the major lobe. So this is the major lobe. So all the parameters will be defined with respect to the major lobe, not with respect to minor lobe. So this is of no use. Are you getting this point or not? A very, very good point about antenna. Okay. So first null beam width also we have seen here. But for that, again, we need to know where is my maximum radiation. So this is about 3 lambda by 2 length antenna. This is a very standard antenna. This is a very standard antenna, 3 lambda by 2. So that's why I took this particular example. Let's make all the patterns. Like I did not make the pattern for lambda by 4. You can do it on your own. For lambda by 4, you can do it on your own. For length equals to lambda, we have already done. For lambda, this was for lambda only, no? Yeah. For lambda, we have already done. For lambda by 4, you can do it on your own. And this pattern, black one, this is for 1.5 lambda. And how it will look in 3D? What will be your H-plane pattern? H-plane pattern will always be a circle. So what will happen is that these 3 lobes will be rotated. Here the diagram is not correct. But this is wrong. Why this is wrong? Because this will be smaller. This width will be smaller. What I mean to say is that what will happen? These wings will be rotated. This wing will also be rotated. All the wings will be rotated 360 degree, right? This wing also be rotated. This wing will also be rotated 360 degree only, right? But no, this is not wrong. This is correct only. Why is this correct? Because what happens is that, what about the circles? We forgot about the circles. Here there will be the biggest circle, but when you go upward, the width of circle is also getting lesser, no? So these wings width is also getting lesser. What I mean to say is that just as you get upward, the radius of circles are also getting lesser. So this is just the multiplication of both of the planes, kind of multiplication you can see. The wings will be rotated, but in a lesser circle. Are you getting this point? So this is how you will get in 3D. So this is correct only. Really sorry, first I said that this is not correct. This is correct only. Okay. So this is how you will get the radiation pattern. So no need to worry if you are not able to understand the 3D view. No one will ask you in the examination. They will never ask you 3D view. They will ask you to draw this one. So will you be able to draw this kind of structure? Yes. This is for lambda equals to 1.5 lambda. Sorry, length equals to 1.5 lambda. This is for length equals to lambda, and this is for length equals to 0.25 lambda, which you will do on your own. Can you do it on your own? For 0.25 lambda, certainly you can do it. So in lambda as well, you are getting one lobe. Into 0.25 lambda as well, you are getting one lobe only. And this is for 1.5 lambda. Okay. So next we are going to do for what? For 1.25 length lambda. Okay. For 1.25 length lambda. But I need to take a break. So you do it on your own. You can certainly do it on your own. Try doing it on your own. If you are able to make the pattern for this one, then this chapter is completely clear to you. So try making the pattern for this one. And this example is mentioned in the Balanis as well. So if some question is coming from radiation pattern, I am 95% sure that it will be asked on 1.25 lambda. Because it is mentioned in Balanis. And mostly question of antenna are framed from Balanis textbook directly. They frame the question from Balanis directly. So in whatever that is mentioned in Balanis, that I am certainly going to cover. In this antenna lecture series, whatever that is mentioned in Balanis and Sadiku, from these two textbooks, whatever that is mentioned, which is in your syllabus, those we are certainly going to cover, because high chances are there that questions will be asked from these topic only. Is that clear? Okay, so I will take a break because it's been a tight discussion of 1 hour. So I need to take a break, but you try it on your own. And you will not need to do the mathematics of this particular analysis. Why is that so? What I am saying is that for finding the position of nulls, you will not need to do the mathematics, because mathematics is already done here. Okay, the same mathematics. I just put the mathematics of that particular example here. So mathematics is already done. So you try doing it on your own. But let me check one thing, if this diagram is correct, because here the next value of null you are getting it. Yeah, this diagram is correct only. Okay. I was just checking the location of null. Like here you are one null you are getting at 0 degree, another null you are getting at more than 60 degree, right? Roughly around more than 60 degree, which is your 70.52 degree only. So this is my 70.52 degree, 70.52 degree, and this would be my first null beam width. So let's not make the diagram more complex. So from here you can see the location of nulls as well. So another location is also there, these locations are also there. So mostly in the examination they can ask you that how many nulls are there, how many lobes will be there. From 0 to 180 degree, how many lobes will be there, how many nulls are there. They can ask you the position of nulls. They can ask you the first null beam width as well, but certainly they will mention where is the maximum radiation. That in the examination they can say that for a particular type of antenna, we are getting the position of nulls at 70.50 degree, 109.470 degree, 0 degree and 180 degree, and the maximum radiation is in the direction of 35 degree and 145 degree. The maximum radiation is in the direction of 35 degree and 135 degree and 145 degree. So what will be your first null beam width? So you will get to know that okay, this is first null, second null, third null, fourth null. You will make this diagram and you will say that okay, this is the direction of maximum radiation. That means this width I need to take. So answer will be 70.52 degree. Is that clear to you? Well and good. So try making the diagram for this one. Try making the diagram for this one. Let me take a pause now. Okay, so did you try this expression? Like, did you try finding the radiation pattern? So what we are going to do, we need to find the normalized value of E field. That will be cos beta is 2 pi by lambda into 1.25 lambda by 2. So that will be cancelled. So it will become 1.25 pi. So 1.25 pi cos theta is equals to cos 1.25 pi divided by sin theta. Now if you are thinking that sir, why randomly you are taking this example, I am taking this example because this is mentioned in Balanis. So if everything that is mentioned in Balanis, that we need to do. So position of nulls, for that what we need to do, we need to put this equals to 0. So if I put this equals to 0, then what I am getting, cos 1.25 pi cos theta is equals to cos 1.25 pi. So this calculation we have done previously. So what we have done, this calculation is previously solved. Previously solved. So when previously is solved, what we are getting, values of theta 53.13, or we can directly copy it. Cannot copy it. 53.13. Another one is 180, no? So another one is 180, but for the rest I need to use calculator. So 180 minus 53.13, 126.87, and the other one is 180 degree. So these are the position of nulls. So from here you need to make the pattern. Now how will you get to know that in this direction, in this particular direction I am having the maximum radiation? Like there will be 3 lobes, you understood, right? 0 degree, 53.13, 126.87 and 180. So one lobe, another lobe and a third lobe. But here in this direction you are having the maximum radiation. So that is something which you cannot predict. You need to put values, you need to put random value. Theta equals to 90 degree. Since this is 53.13, so I will try putting 0, 53.13. I will try putting theta equals to 30 degree. Roughly around 30 degree I will try to put. And here I will put theta equals to 90 degree. So in this expression I will put theta equals to 30 degree and theta equals to 90 degree. So let's try. If I put theta equals to 30 degree here, so that would be under root 3 by 2. Oh, okay, very complex calculation it would be. But let's try. So if I put theta equals to 30 degree, what value I get? So cos 30 I already know this is 0.863 into 1.25 into pi. In radian I am calculating. cos. But again I am telling, mostly there is very high chance that they will give this particular value. Okay, very high chance. So 0.966 and now 1.25 into pi cos minus 0.996 divided by sin 30. So around 3.4 I am getting, I guess. And there can be some calculation error. And at 90 degree, what I am getting? Sin 90 is 1, cos 90 is 0. So cos 0 is 1 minus cos 1.25, 2 into 5 cos. Yeah, there is some calculation error. I'm finding some error in calculation. So you just put theta equals to 30 degree at theta equals to 90 degree. You can check. You will get to know that you are having more radiation in theta equals to 90 degree. Okay, but no one will ask you this thing. Okay, in the examination you will never have to put these values. They will mention, if they want to frame some question, they will mention it. So this is how the pattern will look like, right? There will be three lobes. There will be three lobes like this, and this is theta equals to 0. We are starting till 180. We are going, and from here as well 0 to 180. So there are three lobes, and if you mention the nulls, so this will be one of the null. This will be another null. So what will be the location of this null? That is 53.13. And what will be the location of this null? That is 126.87 degree. And these are also the nulls. But what is your matter of concern here? Matter of concern is the maximum radiation. So this is your major lobe. What is your major lobe? This is your major lobe. So if I ask you, what is your first null beam width here? First null beam width. So you will always look at this major lobe. 53.13 minus 126.87. 126.87 minus 53.13 degree. So 126.87 minus 53.13, 73.74 degree. So this is the first null beam width. But certainly if they want to ask you the first null beam width, then they will certainly say that at theta equals to 90 degree you are getting your maximum radiation. So you need to know whether the maximum radiation is between these two nulls or these two nulls or these two nulls. Okay, or they can simply ask you the location of nulls: 0 degree, 53.13 degree, 126.87 degree and 180 degree. This will be the 3D diagram, because all these lobes will be in circular manner, and it will keep on going upward in the circular manner. All these lobes will be there. So this is the 3D diagram. So this is the picture from the textbook only. This is the picture from Balanese textbook only. So if any kind of length is given, will you be able to make these kind of radiation pattern? Say yes or no. Certainly you will be able to make these kind of radiation pattern if any kind of length is given, right? Let's start studying about monopoles now. So that is very easy. What do we need to study? Quarter wave monopole. We need to make the radiation pattern for base fed linear antenna, or you can say monopole antennas. So this is your monopole. Quarter wave monopole antenna is there. So whenever I see monopole, what do? I will always take the mirror image. I will always take the mirror. So what it has become? Effectively it has become, or let me make the separate diagram because you will be getting confused. So what will be the equivalent of this? The equivalent will be this. I can directly copy here. This I can directly copy here, and this will be the equivalent. So radiation pattern will be same as lambda by 2 dipole, right? Is that statement correct? No, this statement is half correct. It will be same as lambda by 2 dipole, but I know that for monopole, what is my range of theta? It is from 0 to 90 degree only. So it will be same as lambda by 2 dipole, but for the range 0 degree to 90 degree. So I told you one thing, whenever quarter wave monopole is given, you always need to think about lambda by 2 dipole only. If lambda by 8 monopole was given, then what I would be thinking? Lambda by 4 dipole. So all things will be with respect to lambda by 4 dipole only, but power radiated and radiation resistance will be half, and when I draw the radiation pattern, then I need to draw it till 90 degree only. So what I can do is that I can copy my lambda by 2 wavelength. Where did I make the radiation pattern for lambda by 2? Yeah, so this is the radiation pattern for lambda by 2, right? So this is the radiation pattern for lambda by 2. So I can copy the complete pattern. But what I need to do, if I copy the complete pattern, after that what I need to do is that, what I am making the radiation pattern for lambda by 4 monopole. So I can copy the complete pattern, but what I need to erase, the lower part. But because here only 0 to 90 degree will be in action. So, and this also I need to make it better. How I can make it better is that इसको erase करना है, पूरा ही जाएगा. Basically my antenna is also placed like this. Here my antenna is also placed above the ground. Antenna is also placed like this. And for radiation pattern, what I need to do? For radiation pattern, I need to do this one only. That means till 0 to 90 degree only I will make the radiation pattern. That's it. Is that clear to you? All good? Okay. Yeah. And if I make the 3D diagram, then how it will be looking like? 3D diagram. If I make the 3D diagram, then this portion will be gone. Which portion will be gone? This red portion, the lower portion will be gone. Basically 3D diagram will be from 0 to 90 degree only. From 0 to 90 degree. Previously also 0 to 90 degree. Here also 0 to 90 degree. 0 to 90 degree. 0 to 90 degree. But after 90 to 180, everything will be gone. This will not be there. Is that clear to you? So this is how the 3D diagram will look like. Okay. So this is very simple. Just in case of just again, yeah, okay. Just in case of monopole, you just need to erase the lower part. Can you do this thing? You need to draw the radiation pattern for lambda by 8, lambda by 2 and 3 lambda by 4. So what you need to do for monopole antenna? So what I will draw? Draw radiation. What this is equivalent to? This is equivalent to radiation pattern for, what is the double of this? Lambda by 4. What is the double of this? Lambda. And what is the double of this? 3 lambda by 2. Length antenna, length dipole antenna. Draw the radiation pattern for lambda by 4, lambda and 3 lambda by 2 length dipole antenna, but for 0 degree to 90 degree only, right? Here also I made it from 0 to 90 degree only. Is that clear to you or not? So this is your E-plane pattern which I have made. Here also we will draw the same E-plane pattern, but we have already done it. This diagram we are already having, right? So what I need to do, I just need to copy this diagram. I will just copy this diagram, although there are a lot of error in this diagram actually. I copied it from internet somewhere. Okay, I just got it from internet somewhere. So they have made these angles wrong. These angles are wrong. This will be 0 degree actually. So just a second. अरे भाई यार, just a second, sorry for the delay. So these angles are wrong. Don't look at these angles. So do I have the radiation pattern for 0.25 degree? Sorry, 0.25 lambda. Yes. Do I have the radiation pattern for lambda? Yes. Do I have the radiation pattern for 3 lambda by 2? Yes. But I need to make it for 0 to 90 degree only. That means this complete lower part will be gone. Complete lower part will be gone. So this will be the pattern. Complete lower part will be gone. So this will be the pattern. Basically starting from 0 degree to 30 degree to 60 degree to 90 degree. But the lower part will be completely gone. Okay. And this is your 90 degree. Lower part will be completely gone. So if they are asking for monopole, then double the length, make for dipole, and then just remove the lower part. That's it. Okay. Now, what if they ask for 0.4585 lambda? Why you are taking this random value? Because it is mentioned in Balanis. This is the reason why I have taken a very random value for monopole antenna, because this is mentioned in Balanis, and you wouldn't be surprised if they ask you the radiation pattern on monopole antenna, then they can ask this value as well. So since it is mentioned in the Balanis, I don't know what is the specific reason behind taking this random value 0.4585, but since this is mentioned in Balanis, that's why we are seeing the pattern. So what we are going to do, make the radiation pattern for 0.4585 lambda into 2. Just double the length, make the radiation pattern for 0.4585 lambda into 2 dipole antenna for theta equals to 0 degree to 90 degree. That's it. Okay. Yeah. Well and good. So yeah, that's it about our radiation pattern. Nothing more can be asked from this particular topic. And believe me, I will be using the reference of radiation pattern in the next lecture a lot of times. So in the next lecture, again and again, I will be saying that have you seen the radiation pattern? Have you seen that radiation pattern? Okay, so these kind of things I will be using in the next lecture. And again, I will draw some radiation pattern there, and we will make some very good conclusion out of that. So that's it about our linear dipole antenna. I hope I have given the enough concept. We have drawn enough radiation pattern. We have seen the formulas E theta s, H phi s, P average, P radiated. Anything if they wanted to ask on linear dipole antenna or on Hertzian dipole antenna, you will be able to answer that. Say yes or no. Now next lecture is very important. There we are going to discuss the antenna characteristics, or you can say antenna parameter. So first parameter is the radiation pattern, half power beam width and full null beam width. So we have studied about these three parameters already. The next one will be radiation intensity. Then we will study about directive gain. Then we will study about directivity. Then we will study about efficiency. Then we will study about power gain. With that, our lecture will be completed and we will solve a lot of problems. After that, we will see Frisch equation. So with that, our antenna theory will be completed. After that, we need to study antenna array. So this will be the flow of our upcoming lectures. Okay. So antenna is you needlessly find it tough. It is very easy if you follow a certain procedure in studying the antenna. So in that manner, we are going to proceed. Okay then, thank you very much. If you found it helpful, certainly I will be expecting some comments from your side.